Space telescope, the Hubble Deep Field. A small patch of sky no bigger than a grain of sand held at "we open on darkness." Not the darkness of a closed room or a moonless night, but the profound darkness of space itself. A darkness so complete, so absolute, that it contains within it more light than all the cities on Earth could ever produce. We are looking at a photograph taken by the Hubble arm's length, roughly 1/24 millionth of the entire sky. Within this tiny square of cosmic real estate, approximately 3,000 galaxies shine back at us across impossible distances. Each point of light in this image is not a star, but an entire galaxy containing hundreds of billions of stars. Our own Milky Way galaxy harbors between 100 and 400 billion stars, and most galaxies in the observable universe fall within this same order of magnitude. The light we're seeing from these distant galaxies left them when the universe itself was young. Some of these photons have been traveling toward us for more than 13 billion years, crossing a void so vast that human language struggles to contain it. To put this in perspective, 13 billion years ago, Earth did not exist. Our sun did not exist. The atoms that would eventually form our bodies were still scattered across interstellar space, waiting to be gathered by gravity into new stars and planets. This is a documentary about distance, not the kind of distance you can drive or even fly, but distances that break our intuitions, that shatter our everyday understanding of space and time. Distances measured in light years, the amount of space that light itself, traveling at 2,992 kilometers per second, or 186,282 miles per second, can cross in a year. In 1 year, light travels approximately 9.46 trillion kilometers, or 5.88 trillion miles. Light years are the currency of cosmic measurement, and they reveal a universe far stranger and more magnificent than we ever imagined. Consider this. When you look at the sun, you are seeing it as it was 8 minutes and 20 seconds ago. The sun sits approximately 150 million kilometers, 93 million miles, from Earth, a distance astronomers call 1 astronomical unit, or AU. The light takes 8 minutes and 20 seconds to traverse this distance and reach your eyes. The sun could have vanished 8 minutes ago, and you would still see it shining in the sky, blissfully unaware that it was already gone. This delay, this cosmic lag between event and observation, is our first hint that the universe operates on scales we are not built to comprehend. Now, extend that principle outward. The nearest star to our sun, Proxima Centauri, is 4.24 light-years away, a distance of roughly 40 trillion kilometers, or 268,000 times the distance from Earth to the sun. That, just over 4 light-years, conceals an almost unthinkable gulf. If you could travel at the speed of light, which nothing with mass can do according to Einstein's special theory of relativity, it would take you 4.24 years to reach it. The fastest spacecraft humanity has ever built, the Parker Solar Probe, reaches speeds of approximately 700,000 kilometers per hour relative to the sun. At that speed, it would take nearly 6,500 years to reach Proxima Centauri. The Voyager 1 spacecraft, launched in 1977 and now traveling at about 61,000 kilometers per hour, would need more than 73,000 years to cover the same distance. The nearest star is unreachable by any technology we currently possess or can reasonably imagine developing in the next century. But Proxima Centauri is our neighbor. It is practically in our backyard by cosmic standards. The Milky Way galaxy, our home galaxy, is approximately 100,000 to 120,000 light-years across and contains an estimated 100 to 400 billion stars. This means that light starting from one edge of our galaxy would take 100,000 years to reach the other edge. The galaxy is so large that civilizations could rise and fall, species could evolve and go extinct. Entire ice ages could come and go on Earth in the time it takes light to traverse it. Our sun, located about 26,000 light-years from the galactic center, orbits the Milky Way once every 225 to 250 million years, a period astronomers call a cosmic year or galactic year. And yet, The Milky Way is just one galaxy among an estimated 200 billion to 2 trillion galaxies in the observable universe. The estimates vary as our telescopes peer deeper into space and our census of the cosmos becomes more complete. The nearest large galaxy to ours, Andromeda, also known as M31, is approximately 2.537 million light-years away and contains roughly 1 trillion stars. The light we see from Andromeda tonight left that galaxy 257 million years ago, when our ancestors, early members of the genus Homo, were just beginning to walk upright on the African savanna, using primitive stone tools and living in small groups. We are seeing ancient light that carries information about the distant past. Interestingly, Andromeda is one of the few galaxies actually moving toward us rather than away, and it will collide with the Milky Way in approximately 4.5 billion years, merging to form a giant elliptical galaxy that astronomers have playfully nicknamed Milkomeda. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, extends about 46.5 billion light-years in every direction from Earth. This creates an observable sphere with a diameter of approximately 93 billion light-years. This figure seems to violate what we just said about the universe being about 13.8 billion years old. How can light have traveled 46.5 billion light-years in only 13.8 billion years? The answer lies in the expansion of the universe itself. Space itself has been stretching while that light has been traveling, carrying distant galaxies away from us faster than light itself can catch up. The fabric of space-time itself expands, and this expansion is not limited by the speed of light, because nothing is actually moving through space faster than light. Rather, space itself is growing. This is where our intuitions completely fail us. We think of space as a static stage on which events unfold, but space itself is dynamic, expanding, carrying galaxies with it like raisins in rising bread dough. The current rate of this expansion is described by the Hubble constant, measured at approximately 70 kilometers per second per megaparsec. What this means is that for every megaparsec of distance, about 3.26 million light-years, space expands at a rate of 70 kilometers per second. A galaxy 10 megaparsecs away recedes from us at 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second, and so on. The most distant galaxies we can see are receding from us at speeds approaching and even exceeding the speed of light, not because they're moving through space that quickly, but because the space between us and them is expanding. Let us consider a photon of light that left a distant galaxy 13 billion years ago, shortly after the formation of the first stars and galaxies in the universe. It has been traveling toward us all that time at 299,792 kilometers per second, but the galaxy it left has been carried away by the expansion of space. That galaxy is now more than 30 billion light-years away from us, even though its light has only been traveling for 13 billion years. The photon has been swimming against a current of expanding space, and the shore it left is now much farther away than when it started. This creates the counterintuitive situation where we can see objects that are now much farther away than the travel time of their light would suggest. These distances create profound consequences for what we can know about the universe. When we look at distant galaxies, we are not seeing them as they are now. We are seeing them as they were billions of years ago. We are looking backward in time, seeing a younger universe. Those galaxies have evolved, changed, perhaps merged with other galaxies, perhaps even died in the eons since their light left them. But we cannot know this. We cannot receive any signal from them about their current state faster than the speed of light allows. They exist for us only in the past, frozen in time at the moment their light began its journey toward us. This creates a kind of cosmic horizon, a boundary beyond which we cannot see, not because there's nothing there, but because light from beyond that horizon hasn't had time to reach us yet in the 13.8 billion years since the Big Bang. And due to the accelerating expansion of the universe, discovered in 1998 through observations of distant type Ia supernovae, There are regions of space that we will never be able to see, no matter how long we wait. The light from those regions will never catch up to us. They are forever beyond our cosmic horizon, causally disconnected from us in every meaningful sense. Imagine standing on a beach watching the ocean. Now, imagine that the water is receding from you, and the rate at which it recedes increases with distance. Nearby water moves slowly away, perhaps a few centimeters per second, but water farther out races away from you at meters per second, and water at the horizon retreats at speeds measured in kilometers per second. Eventually, you reach a point where the water is receding faster than you can possibly run toward it, even if you could run at Olympic speeds. That water is forever unreachable, separated from you by an insurmountable barrier, not of distance alone, but of relative velocity. This is the situation we face with the expanding universe, except the speeds involved are not meters per second, but significant fractions of the speed of light itself. The astronomer Edwin Hubble discovered this expansion in 1929, working at the Mount Wilson Observatory in California with a 100-inch Hooker telescope, then the largest telescope in the world. He observed that distant galaxies showed spectral lines shifted toward the red end of the spectrum, indicating they were moving away from us. Furthermore, he found that the farther away a galaxy was, the faster it was receding, a relationship now called Hubble's law. For every megaparsec of distance, he found that recession velocity increased by approximately 500 kilometers per second, though modern measurements have revised this down to about 70 kilometers per second per megaparsec. This relationship, linear and universal, was the first evidence that the universe itself was expanding, supporting the theoretical predictions of Georges Lemaitre's Big Bang model. But Hubble could only observe relatively nearby galaxies, cosmic neighbors within a few hundred million light-years, limited by the technology of his era. Modern telescopes have pushed that boundary much farther. The Hubble Space Telescope, named in Edwin Hubble's honor and launched in 1990, has peered back to galaxies that existed when the universe was only 400 to 800 million years old, roughly 3 to 6% of its current age. The James Webb Space Telescope, launched in December 2021 and positioned at the second Lagrange point 1.5 million kilometers from Earth, can see even farther, detecting light from galaxies that formed when the universe was barely 200 to 300 million years old, in the epoch astronomers call cosmic dawn. These galaxies existed when the universe was less than 3% of its current age, and their light has been traveling toward us for more than 13.5 billion years. These observations reveal a universe very different from our own. The early galaxies were smaller, more chaotic, more compact, filled with massive hot stars that burned blue and white, stars that lived fast and died young in spectacular supernova explosions after only a few million years. The universe was denser then, with matter concentrated in a smaller volume, and galaxies collided and merged more frequently, building up larger structures through hierarchical assembly. The light from these ancient galaxies has been stretched by the expansion of space during its long journey, shifted from visible and ultraviolet light into the infrared portion of the spectrum, what astronomers call cosmological redshift. An object with a redshift of Z Curie 10, for example, has had its light wavelength stretched by a factor of 11. This is why the James Webb Space Telescope, with its 6.5-meter primary mirror optimized for infrared observations, can see these distant galaxies so clearly when optical telescopes struggle. But even these earliest galaxies are not the edge of the observable universe. Beyond them lies the cosmic microwave background, CMB, the afterglow of the Big Bang itself. This radiation, released when the universe was only 380,000 years old and had cooled enough for electrons and protons to combine into neutral hydrogen atoms, a process called recombination, has been traveling toward us for more than 13.4 billion years. It surrounds us on all sides, a shell of ancient light that represents the farthest we can possibly see with electromagnetic radiation. The CMB has a temperature of 2.725 Kelvin, just 2.2 degrees above absolute zero, cooled by the expansion of the universe from its initial temperature of approximately 3,000 Kelvin at the moment of recombination. The cosmic microwave background is remarkably uniform, the same temperature in all directions to within 1 part in 100,000, with tiny fluctuations of only about 0.0201 degrees. This uniformity posed a significant problem for cosmologists in the 1980s and early 1990s. How could regions of space separated by more than 90 degrees on the sky, regions that were never in causal contact with each other, meaning light couldn't have traveled between them in the time available, be at exactly the same temperature? Without some mechanism to bring them into thermal equilibrium, we would expect random temperature variations much larger than what we observe. The solution, proposed by physicist Alan Guth in 1980, was cosmic inflation, a brief period in the universe's first fraction of a second, specifically between approximately 1036 and 1032 seconds after the Big Bang, when space expanded exponentially, growing by a factor of at least 10 to the power 26 and possibly much more in an infinitesimal moment. This is equivalent to something the size of an atom expanding to the size of a galaxy in much less than a blink of an eye. Inflation solved the uniformity problem by proposing that all the regions we can see today were once close together, perhaps smaller than a subatomic particle in thermal equilibrium, before inflation blew them apart faster than light could travel between them. The entire observable universe, with its 93 billion light-year diameter, originated from a region smaller than a grain of sand, or perhaps even smaller than a proton. But inflation also has profound implications for the scale of the total universe. If inflation occurred as the theory suggests, then the universe beyond our observable horizon is vastly, perhaps infinitely, larger than the part we can see. Conservative estimates suggest the entire universe could be at least 10 and 23 times larger than the observable universe, while some models suggest it could be infinite. Our observable universe might be an infinitesimal bubble in an inconceivably larger cosmos. Consider an analogy. Imagine Earth, but you can only see 1 mile in any direction due to a permanent fog that extends from the ground to high in the atmosphere. You might map your visible region carefully, noting every hill, valley, stream, and tree within your 1 mile radius. But you would have no direct information about what lies beyond the fog. The Earth could be a small island 5 miles across, or it could be a vast continent, or even a planet with a circumference of 40,000 kilometers. You simply cannot know from your limited vantage point. Our situation with the observable universe is precisely analogous. We can map our cosmic neighborhood extending 46.5 billion light-years in every direction, but what lies beyond our horizon remains fundamentally unknown and unknowable with our current observational capabilities. This leads to one of the most profound questions in cosmology. Is the universe finite or infinite? Measurements of the cosmic microwave background by satellites like WMAP and Planck suggest that the universe is very close to geometrically flat with a curvature parameter O within 0.4% of exactly 1.0. A flat universe, according to general relativity, is spatially infinite. If the universe is truly infinite, then it contains an infinite number of stars, far more than the 1024 in our observable universe, an infinite number of planets, an infinite number of galaxies. And given infinite space combined with quantum mechanics and the finite number of ways particles can be arranged, there would necessarily be an infinite number of regions identical to ours, an infinite number of copies of Earth, and an infinite number of copies of you, reading this exact sentence at this exact moment. Somewhere, infinitely far away beyond our cosmic horizon, there is another you, making different choices, living a different life, in a universe region identical to ours down to the quantum level. This is not science fiction, but a serious consequence of infinite space combined with the statistical mechanics of matter arrangement. The distances we've discussed so far are all within the observable universe, the region from which light can reach us. But what about the universe beyond that horizon? Due to the accelerating expansion of space, driven by the mysterious dark energy that comprises approximately 68% of the universe's total energy content, with dark matter comprising another 27% and ordinary matter just 5%, galaxies beyond our current horizon are being carried away from us faster than light can travel. We will never see them. They are not just far away, they are fundamentally inaccessible, forever beyond our reach no matter how advanced our technology becomes. This means that the observable universe is shrinking in a certain sense. The volume of space within our horizon is growing, yes, but the number of galaxies we can potentially observe is decreasing over time. Galaxies that we can see today will eventually cross our cosmic horizon and disappear from view, their light redshifted into oblivion, the wavelength of their photons stretched to infinity. In the far future, hundreds of billions of years from now, current estimates suggest around 150 billion years, only the galaxies in our local group, about 54 galaxies including the Milky Way and Andromeda, gravitationally bound together within a region about 10 million light-years across, will be visible to astronomers. An astronomer in that distant epoch would see a universe containing only a few dozen galaxies, surrounded by complete darkness. They would have no evidence that the universe was once filled with hundreds of billions of galaxies. They would have no evidence of the Big Bang, because the cosmic microwave background would have been redshifted beyond any possible detection, its temperature indistinguishable from absolute zero. They would construct a cosmology based on a static, nearly empty universe containing only their local galactic group. They would be completely wrong about the nature and history of the cosmos, but they would have no way to know it. Their observations would be consistent with an incorrect model. This should give us pause. What evidence has already disappeared beyond our horizon? What could we have learned about the universe if we had been here earlier, before expansion carried that information away forever? What fundamental truths about reality are we missing because we happen to exist at this particular epoch in cosmic history? The philosopher Immanuel Kant wrote in his 1790 work Critique of Judgment about what he called the sublime, experiences that overwhelm our capacity to comprehend them, that remind us of how small and powerless we are in the face of nature's vastness. He had in mind mountain peaks rising thousands of meters into the sky and storm-tossed oceans stretching to the horizon. But these are nothing compared to the cosmic sublime, the overwhelming vastness of space and time revealed by modern astronomy. Mount Everest rises 8,149 meters above sea level. The Pacific Ocean extends perhaps 19,000 kilometers at its widest. Mountains can be climbed, oceans can be crossed. But light years, distances of trillions upon trillions of kilometers, represent gulfs that are not just practically, but fundamentally beyond our reach given the laws of physics as we understand them. And yet, remarkably, we have measured these distances. We have mapped the universe to scales that our ancestors could not have imagined, could not even have conceived of in their wildest dreams. The ancient Greeks, including philosophers like Aristotle, knew that the stars were far away, but they imagined them attached to a crystalline celestial sphere just beyond the orbit of Saturn, perhaps a few million kilometers distant. Medieval and Renaissance scholars debated whether the stars were millions of miles away or billions of miles away, representing the outer boundary of creation. They were off by factors of trillions, underestimating cosmic distances by margins that strain comprehension. The first person to successfully measure the distance to a star other than the Sun was Friedrich Bessel, a German astronomer and mathematician who in 1838 used the parallax method to determine that the star 61 Cygni was approximately 10.3 light-years away. Modern measurements put it at 11.4 light-years. Parallax is the apparent shift in a star's position against the background of more distant stars as Earth orbits the Sun, creating a baseline of 2 AU, 300 million kilometers. It's the same effect that makes your thumb appear to move against the background when you close one eye and then the other, with your eyes providing a baseline of about 6 centimeters. But stellar parallax is incredibly tiny, less than 1 arcsecond for even the nearest stars. 1 arcsecond is kin 3600 of a degree, the angle subtended by a United States dime seen from a distance of 2.2 miles, or the angle subtended by a human hair at a distance of 10 meters. Measuring such tiny angles required telescopes of extraordinary precision, requiring careful correction for atmospheric effects, thermal expansion of the telescope, and countless other sources of error. It required observers of enormous patience, taking measurements over many months as Earth moved from one side of its orbit to the other. But Bessel succeeded after years of painstaking observation, and for the first time in human history, we had a direct geometric measurement of cosmic distance based on trigonometry and the known diameter of Earth's orbit. The universe was no longer a matter of philosophical speculation or religious doctrine, but quantifiable, measurable fact. And that fact was humbling. Even the nearest stars were so far away that their light took more than a decade to reach us, traveling at the fastest speed possible in the universe. Since Bessel's time, astronomers have developed a cosmic distance ladder with multiple rungs, each method extending our reach farther into space while building on the measurements from the previous rung. Parallax works reliably for stars within about 100 to 300 light-years with ground-based telescopes, and the Gaia space mission has extended this to several thousand light-years for bright stars. For more distant stars within our galaxy, we can use standard candles, objects whose intrinsic brightness we know, allowing us to calculate their distance by comparing their known luminosity to their observed brightness using the inverse square law of light, Cepheid variable. Stars, which pulsate with periods ranging from 1 to 100 days, serve as excellent standard candles because their pulsation period is directly related to their intrinsic luminosity, a relationship discovered by Henrietta Swan Leavitt in 1912. A Cepheid with a 10-day period is intrinsically brighter than one with a 3-day period, and we can calculate exactly how much brighter. Edwin Hubble used Cepheid variables to measure the distance to Andromeda in 1924, determining it was approximately 900,000 light-years away, later refined to 237 million light-years with better measurements, proving conclusively that it was a separate galaxy far beyond our Milky Way, and settling the great debate about the nature of spiral nebulae. For even greater distances, beyond about 100 million light-years where individual Cepheids become too faint to observe, astronomers use type Ia supernovae, exploding white dwarf stars that reach approximately the same peak brightness, about 5 billion times brighter than the Sun. These cosmic explosions can be seen across billions of light-years, making them ideal for mapping the universe's expansion history. It was observations of type Ia supernovae in distant galaxies in the late 1990s that revealed the accelerating expansion of the universe, contradicting expectations and forcing cosmologists to introduce the concept of dark energy. This discovery shocked the scientific community and earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics. Each rung on this cosmic distance ladder has its own uncertainties and systematic errors, typically 5 to 10% for most methods, and these uncertainties accumulate as we climb higher and rely on more assumptions. The distances to the farthest galaxies, measured using cosmological models and redshift relationships, are therefore less certain than the distances to nearby stars measured with parallax. But even accounting for these uncertainties, the picture is unambiguous. The universe is staggeringly, almost incomprehensibly large, with a scale that defies human intuition. Let us return to where we began, to that Hubble Deep Field image showing approximately 3,000 galaxies in a tiny patch of sky covering only 1/24,000,000 of the celestial sphere. Now, consider that the Hubble Space Telescope could point at any random patch of apparently dark sky, anywhere in any direction, and see essentially the same thing: thousands of galaxies stretching back through billions of years of cosmic history. The universe is filled with galaxies uniformly in every direction, at every distance, as far as we can see, what cosmologists call homogeneity and isotropy. And each of those galaxies contains hundreds of billions of stars, each star potentially orbited by planets, each planet potentially harboring life. The total number of stars in the observable universe is estimated at approximately 10 to the minus 24, or 1 septillion. That's thousand stars written as a 1 followed by 24 zeros. To put this in perspective, this is more stars than all the grains of sand on all the beaches and deserts of Earth combined, which number roughly 1023. And each of those stars is separated from its neighbors by distances measured in light years, typically several light years for stars within a galaxy like ours. The universe is not just large, it is almost entirely empty space, a vast void punctuated by rare islands of matter. The average density of matter in the universe is approximately 5.9 protons per cubic meter, less than the best vacuum we can create in laboratories on Earth. This emptiness is not incidental but crucial to the universe's structure and to the possibility of stable planetary systems and life. If stars were closer together, separated by only light months instead of light years, their gravitational interactions would destabilize planetary orbits over millions of years, making stable systems like our solar system impossible to maintain. If galaxies were packed more tightly, collisions would be more common, disrupting the orderly rotation of galactic disks and stirring up stars into chaotic orbits. The vast distances between celestial objects are not a bug, but a feature, essential to creating the stable cosmic architecture that allows planets to orbit stars for billions of years, giving evolution time to work its patient magic. We are left with a profound paradox that lies at the heart of our cosmic existence. We are connected to the most distant galaxies visible in our telescopes by the light they emit, by the shared laws of physics that govern both us and them, by the fact that we emerged from the same Big Bang 13.8 billion years ago, assembled from the same primordial hydrogen and helium. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in the cores of stars that lived and died billions of years ago, their matter scattered into space to eventually coalesce into our solar system. We are, quite literally, made of star stuff, as Carl Sagan eloquently observed, and yet we are separated from these distant galaxies by distances so vast, by gulfs so profound that we can never visit them, never send signals to them that could arrive before they disappear beyond our cosmic horizon, never communicate with any civilizations that might exist among their hundreds of billions of stars, never know them as they are now, but only as they were in the ancient past. We are cosmically alone, adrift on a small planet, 12,742 kilometers in diameter, orbiting an average star of spectral class G2V in an ordinary spiral galaxy containing 100 to 400 billion other stars, surrounded by a universe too large for us to ever fully explore, too ancient for us to ever fully comprehend, too magnificent for us to ever fully grasp. We can measure it, map it, photograph it, and model it, but we cannot, in any meaningful physical sense, ever leave our tiny corner of it. The cosmic distances are too vast, the expansion too relentless, the speed of light too slow relative to the scale of the universe. We are observers, not travelers, in this cosmic ocean, witnesses to a grandeur we can see but never touch. In the darkness between galaxies, in regions containing on average less than 1 atom per cubic meter, something extraordinary happens. Photons that left distant stars billions of years ago continue their lonely journey across space, traveling through voids so empty that they might encounter only a handful of hydrogen atoms in a volume the size of a cathedral. These wandering particles of light, each carrying 1.8 to 3.1 electron volts of energy if they started as visible light, carry information encoded in their wavelength, their energy, their trajectory, even their polarization. They are messengers from the past, and when they finally arrive at Earth after journeys lasting longer than our species has existed, colliding with the sensors of our telescopes, photomultiplier tubes, CCD arrays, or infrared detectors cooled to within degrees of absolute zero, they tell us stories about events that occurred long before dinosaurs walked the Earth, before the first fish crawled onto land, before Earth itself coalesced from the protoplanetary disk around our young sun. But these stories are not always easy to read. The light has changed fundamentally during its journey through expanding space. It has been stretched by the expansion of the universe itself, shifted toward redder, longer wavelengths in a phenomenon called cosmological redshift. This is distinct from Doppler shift, though superficially similar. The photons aren't moving away from us through space. Rather, the space itself is expanding, stretching the wavelength of the light like ink on a balloon being inflated. The degree of this redshift, denoted by the letter Z, tells us how far the light has traveled and how much the universe has expanded since the photon began its journey. A galaxy with a redshift of Z1 existed when the universe was approximately 6 billion years old, roughly 44% of its current age. Its light has been traveling toward us for about 7.7 billion years, and the wavelength of that light has been doubled by the expansion of space. What left the galaxy as blue light at 450 nanometers arrives at Earth as red light at 900 nanometers, shifted into the near-infrared. A galaxy with a redshift of Z2 existed when the universe was only 3.3 billion years old, about 24% of its current age. A galaxy with Z6, near the limit of what Hubble can observe, existed when the universe was barely 1 billion years old, less than 8% of its current age, and its light has been traveling for 12.8 billion years. The most distant galaxy confirmed as of early 2025, designated JADES GS Z14 Dauro and observed by the James Webb Space Telescope, has a redshift of Z14 B-32. This galaxy existed just 290 million years after the Big Bang, when the universe was only 2.1% of its current age. The light we're seeing left that galaxy 13.5 billion years ago, and it has been stretched so dramatically that ultraviolet light at 200 nanometers has been redshifted all the way to 3,000 nanometers in the mid-infrared, a stretch factor of 15.32. Every wavelength of light from this galaxy has been elongated by more than 15 times during its journey across the cosmos. This is time travel of a sort, but only backward. We can see the past but cannot visit it. We can observe galaxies as they were billions of years ago, frozen in time at the moment their light departed, but we cannot see them as they are now, in our present moment. For all we know, some of the galaxies we observe tonight in our most powerful telescopes no longer exist in any recognizable form. They might have collided with other galaxies, a process that takes hundreds of millions of years to complete, been torn apart by tidal forces from a massive neighbor, merged into larger elliptical galaxies, or simply exhausted their fuel for star formation and faded into darkness, their stellar populations aging to red giants and white dwarfs. But their light continues toward us at 299 and the length of 92 kilometers per second, unwavering and faithful, carrying an image of what they once were like a photograph from a distant ancestor. The astronomer Vera Rubin, who died in 2016 after decades studying galaxy rotation curves and providing some of the strongest evidence for dark matter, once remarked that we are privileged to live in a time when we are still making fundamental discoveries about the universe. She was referring specifically to dark matter, the invisible substance that comprises 27% of the universe's mass energy, and whose gravitational effects she observed through the unexpectedly flat rotation curves of spiral galaxies. But her observation applies more broadly to our cosmic epoch. We live in a time when the universe is still bright enough to study, when the evidence of the Big Bang hasn't yet been redshifted into complete invisibility, when distant galaxies are still within our observable horizon, when the cosmic microwave background is still detectable at 2.725 Kelvin, rather than having been cooled to 0.801 Kelvin or less. We are cosmically fortunate, in a sense, to exist when we do, in what might be called the universe's middle age. But this luck is profoundly temporary. The universe is not static, and the distances that define its structure are changing every second. Galaxies are moving apart, carried by the expansion of space itself, with recession velocities proportional to their distance from us. The rate of this expansion has not been constant throughout cosmic history, and understanding how it has changed tells us the universe's story. During the inflationary epoch, roughly 10 Ordered 36 to 10 or 32 seconds after the Big Bang, the universe expanded exponentially, doubling in size every 10 or 38 seconds or so, growing by a factor of at least 10.9 in an infinitesimal fraction of a second. This is an expansion rate utterly beyond comprehension. Imagine something the size of a proton inflating to the size of the Milky Way galaxy in far less time than it takes light to cross an atom. After inflation ended, the expansion slowed dramatically, though it never stopped. For the first several billion years, the expansion decelerated as gravity worked to pull matter together, slowing the expansion rate. The universe was matter-dominated during this period, with gravitational attraction fighting against the momentum of expansion. Then, approximately 5 billion years ago, when our Sun and Earth were just forming, something remarkable happened. The expansion began to accelerate again. This acceleration is driven by dark energy, the mysterious component that comprises approximately 68% of the universe's total energy content. Dark energy is one of the great mysteries of modern physics, arguably the most profound puzzle confronting cosmology today. It appears to be a property of space itself, perhaps related to the quantum vacuum energy predicted by particle physics, though the predicted value is wrong by a factor of 10 neurotonomkni, the worst prediction in the history of science. Dark energy acts like a kind of negative pressure or anti-gravity that causes space to expand, and crucially, its density appears to remain constant as the universe expands. This means that as space grows, the total amount of dark energy increases proportionally. In contrast, matter becomes more dilute as the universe expands, double the volume, and the matter density halves. But dark energy maintains its density, creating a feedback loop that drives ever-accelerating expansion. Current observations suggest that this acceleration will continue indefinitely, governed by the equation of state parameter W, which describes the relationship between dark energy's pressure and density. If W takes out the 1, corresponding to a true cosmological constant, the acceleration continues forever but at a controlled rate, leading to what cosmologists call the heat death or big freeze scenario. The universe continues expanding forever, growing exponentially in the far future, becoming increasingly cold and dark as stars exhaust their fuel and galaxies spread ever farther apart. The temperature of the cosmic microwave background, currently 2.725 Kelvin, drops toward absolute zero, approaching but never quite reaching it. Eventually, in this scenario, the universe will consist of isolated black holes separated by truly incomprehensible distances. Our Sun will have died about 5 billion years from now, swelling into a red giant and engulfing Mercury and Venus before collapsing into a white dwarf. That white dwarf will cool over trillions of years, eventually becoming a black dwarf, a stellar remnant at essentially the same temperature as the surrounding space. The most massive stars will collapse into black holes during supernova explosions. These black holes will gradually evaporate through Hawking radiation, a quantum process that causes them to emit particles and lose mass at a rate inversely proportional to their mass squared. A black hole with the mass of our Sun would take approximately 1067 years to evaporate completely. A supermassive black hole with 1 billion solar masses, like those found at the centers of large galaxies, would take about 100 years to evaporate. After all black holes have evaporated, the universe will consist of a thin soup of photons, neutrinos, and occasional electrons and positrons at temperatures of perhaps 10 or 30 Kelvin, immeasurably close to absolute zero. The universe will have maximized its entropy, achieved thermodynamic equilibrium, and effectively ended all interesting processes. This will take an incomprehensibly long time. Current estimates suggest 100 years or more, a number so large that writing it out would require 100 zeros. But in a universe without end, all things that can happen will eventually happen, and eternal expansion leads inevitably to maximum entropy. In an alternative scenario called the Big Rip, dark energy increases in strength over time, with W pop 1. If this is the case, dark energy becomes increasingly dominant, eventually becoming so powerful that it tears apart gravitationally bound structures. First, galaxy clusters would be ripped apart, with individual galaxies flying off into isolation. Then, billions of years later, galaxies themselves would be disrupted, stars scattered into the expanding void. Then, solar systems would be torn apart, planets flung away from their parent stars. Eventually, approximately 60 million years before the Big Rip's final moment, planets themselves would be ripped apart, unable to hold themselves together against the exponentially increasing expansion rate. In the final moments, months before the Big Rip, atoms themselves would be disrupted as the expansion rate exceeds the electromagnetic forces binding electrons to nuclei. In the last fraction of a second, even atomic nuclei would be torn apart, protons and neutrons ripped from each other, and ultimately quarks themselves separated. The universe would literally rip itself apart at the most fundamental level. Current observations suggest this scenario is unlikely. Measurements of W from type Ia supernovae and the cosmic microwave background place it at approximately 1.0 plus 0.1, consistent with a cosmological constant, but we cannot rule it out entirely. Our understanding of dark energy remains rudimentary, based on observations of its effects, rather than any deep theoretical understanding of its nature. Either way, whether through heat death or the Big Rip, the long-term future of the universe is cold, dark, empty, or catastrophically disrupted. The brief epoch in which stars shine and life exists, perhaps 100 trillion years from the Big Bang until the last stars die, is a cosmic anomaly, a tiny bubble of complexity and order in an overwhelmingly simple and disordered universe. We exist in the universe's youth, what might be called its stelliferous era, when there is still enough free energy, sufficient temperature differences, adequate gradients to power interesting chemical reactions and complex structures. Give the universe enough time, 10 to 100 years or more, and it will decay inexorably toward maximum entropy and simplicity, a state of perfect equilibrium where nothing interesting can ever happen again. This raises profound questions about meaning and purpose in a universe destined for heat death. If everything we do will eventually be erased by entropy, if Earth itself will be engulfed by the expanding sun in approximately 5 billion years, if the sun itself will fade to a cold cinder over the next 10 trillion years, if even that cinder will eventually decay through proton decay, if it occurs, or black hole evaporation, then what is the point of human endeavor? Why does any of it matter if the ultimate fate of all our achievements is dissolution into a sea of maximum entropy? The philosopher Bertrand Russell grappled with this question in his 1903 essay, A Free Man's Worship, written when the implications of thermodynamics and entropy were beginning to sink into philosophical consciousness. He acknowledged the ultimate futility of human endeavor in the face of cosmic timescales and the heat death of the universe, but argued that this very futility makes our accomplishments more, not less, meaningful. We create meaning and value precisely because the universe provides none intrinsically. We build, love, discover, create, and strive for beauty and truth despite knowing, or perhaps because we know, that it will all eventually end. That is not tragedy. That is defiance. That is humanity asserting its values against an indifferent cosmos. The fact that a symphony will not echo through eternity does not diminish its beauty in the moment it is played. But let us return from these distant futures to the present, to the distances we can actually observe and measure with our current technology. We have discussed light years as a unit of distance, but there's another aspect of light that becomes crucial at cosmic scales: its finite speed. Light travels fast by everyday standards, fast enough to circle Earth's 4075-kilometer equator 7.48 times in 1 second. But space is so vast that even light's tremendous speed of 299,192 kilometers per second becomes insufficient. Light becomes effectively slow at cosmic distances, and this creates fundamental limitations on communication and causality. Consider communication with a spacecraft at the edge of our solar system. The Voyager 1 probe, launched on September 5, 1977, is now more than 24.3 billion kilometers, 15.1 billion miles from Earth as of December 2024, traveling at approximately 61,000 kilometers per hour relative to the Sun. It is currently about 22.5 light hours away, or roughly 165 astronomical units. A radio signal sent to Voyager 1 at the speed of light takes 22.5 hours to arrive, and its response takes another 22.5 hours to return to Earth. Any conversation with Voyager has a 45-hour delay between message and response. The spacecraft is effectively autonomous because real-time control is utterly impossible. By the time we receive data indicating a problem and send a correction, almost 2 full days have passed, and the situation has likely changed completely. The New Horizons spacecraft, which flew past Pluto in July 2015, was approximately 4.5 light hours from Earth at the time of its closest approach, resulting in a 9-hour round-trip communication delay. Mission controllers had to program the entire flyby sequence in advance and hope nothing went wrong, because there was no possibility of real-time intervention. The spacecraft was on its own during the most critical moments of its mission. Now, imagine trying to communicate with a probe at Proxima Centauri, 4.24 light-years away, or approximately 40 trillion kilometers. Send a message. How are things? Report your status. 4 years and 3 months later, traveling at exactly 2,999,792 kilometers per second, the electromagnetic signal arrives at the probe's antenna. The probe's computer processes the request and composes a response. All systems nominal. Continuing observations. 4 years and 3 months after that, we received the reply on Earth. 8.5 years have passed since we asked the question. Any notion of conversation, of back-and-forth dialogue, breaks down completely. Communication becomes more like leaving messages in bottles and casting them into the ocean, hoping they wash up on distant shores decades hence, with any reply taking decades more to return. This has profound implications for any hypothetical interstellar civilization spanning multiple star systems. Even if faster-than-light travel were somehow possible, which our current understanding of physics adamantly suggests it is not, merely communicating across stellar distances would create empires where each star system operates as an effectively independent entity. A government based on Earth could not meaningfully govern a colony at Proxima Centauri, 4.24 light-years away, nor at Alpha Centauri A and B at 4.37 light-years. By the time the colony sent a message asking for instructions on how to respond to an emerging crisis and received a response, 8.5 years would have passed. The situation would have evolved beyond recognition. The crisis would be long resolved or catastrophically worsened, and the received instructions would be obsolete. A colony at Tau Ceti, 11.9 light-years away, would have a 24-year round-trip communication time. A colony at Epsilon Eridani, 10.5 light-years distant, would face a 21-year delay. These are not mere inconveniences, but fundamental restructurings of political possibility. No coherent government can function with multi-decade delays in communication. Each colony would necessarily develop its own laws, customs, governance structures, and eventually its own culture distinct from Earth. After several centuries, the colonies might share a common origin, but would be as different from each other as contemporary nations on Earth are from their founding populations. Science fiction often handwaves this problem with concepts like hyperspace, subspace communication, ansible systems, or quantum entanglement communicators, allowing instantaneous or near-instantaneous transmission of information across light years or even across the entire galaxy. But these are purely fictional inventions with no basis whatsoever in known physics. Einstein's special theory of relativity, published in 1905 and confirmed by countless experiments over more than a century, absolutely forbids transmitting information faster than the speed of light in vacuum. Quantum entanglement, often misunderstood as allowing faster-than-light communication, explicitly cannot be used to send information faster than light. Entanglement allows correlations between distant measurements, but not causal influence. While relativity has been tested extensively and passed every test, from particle accelerators where electrons are routinely accelerated to 0.9999991 times the speed of light, to GPS satellites that must account for both special and general relativistic time dilation to function accurately, to observations of binary pulsars whose orbital decay matches general relativity's predictions to within 0.2%, we cannot absolutely, definitively rule out the possibility of undiscovered physics that might somehow permit faster-than-light communication. But we should not count on it. The speed of light appears to be a fundamental feature of space-time itself, not merely a property of electromagnetic radiation, but a cosmic speed limit embedded in the structure of reality. The speed of light creates a cosmic speed limit that governs not just motion, but causality itself. Events separated by distances greater than light can travel in the time between them, cannot influence each other. They are causally disconnected, existing in each other's elsewhere, a region of space-time that is neither in the past nor the future, but sideways, outside the light cone. This means that the universe does not have a single universal now, no cosmic moment of simultaneity that all observers can agree upon. Different observers, moving at different speeds or in different gravitational fields, will disagree about which distant events are simultaneous, about what is happening right now on the other side of the galaxy or in distant galaxy clusters. This relativity of simultaneity has deeply bizarre consequences. Imagine two galaxies, 1 billion light-years apart, or 9.46 x 10^24 meters. An event occurs in one galaxy. A supermassive star explodes as a supernova, briefly outshining its entire host galaxy at an absolute magnitude of 19. By any reasonable definition, this event happens before the light from the explosion could possibly reach the other galaxy, which will take 1 billion years traveling at light speed. But an observer moving at a different velocity, say 0.1 c relative to the galaxy frame, might measure the events differently. For some observers in some reference frames, the star explodes before a particular event in the distant galaxy. For others moving differently, it explodes after. Both measurements are equally valid. Einstein's relativity tells us there is no absolute ordering of events across such distances unless they are causally connected. This seems to violate common sense entirely, but common sense evolved to navigate the African savanna at speeds of a few meters per second across distances of a few kilometers, not to comprehend the cosmos at speeds approaching light speed across billions of light years. At everyday speeds and distances, relativistic effects are too small to notice. Time dilation at 100 kilometers per hour is approximately 0.001%. But they are real, and at cosmic scales, they dominate. GPS satellites orbiting at 14,000 kilometers per hour and at an altitude of 20,200 kilometers must account for both special relativistic effects, time runs slower for moving clocks by 7 microseconds per day, and general relativistic effects, time runs faster in weaker gravity by 45 microseconds per day. Or they would accumulate errors of approximately 10 kilometers per day. Relativity is not just theoretical speculation, it is practical, observable, measurable, and necessary for modern technology. The implications extend to time travel. If you could somehow travel faster than light through space, relativity shows you could arrive at your destination before you left, measured in certain reference frames, creating a causality violation, an effect preceding its cause. This is one fundamental reason physicists believe faster-than-light travel is impossible. It would allow you to send information into your own past, creating logical paradoxes like the grandfather paradox. The speed of light is not just a speed limit, but a cosmic censorship mechanism, preserving causality and preventing the universe from descending into paradox and contradiction. But there are theoretical loopholes, at least on paper. General relativity permits exotic solutions like wormholes, hypothetical tunnels through spacetime that could connect distant regions of space or even different times. If wormholes exist naturally and can be made traversable, requiring conditions vastly beyond our current technology, You might theoretically be able to travel from one star to another, or even from one galaxy to another, without exceeding the speed of light locally, because you would be taking a shortcut through higher dimensional spacetime, reducing the effective distance. This is the basis for many science fiction stories from Stargate to Interstellar. However, natural traversable wormholes almost certainly do not exist, and creating artificial ones would require exotic matter with negative energy density, matter that gravitationally repels rather than attracts, something we have never definitively observed despite predictions from quantum field theory. The Casimir effect between parallel conducting plates shows that negative energy densities are possible quantum mechanically, but the energies are infinitesimally small, on the order of 10⁻⁷ joules per cubic meter, whereas keeping a wormhole open would require negative energy comparable to the mass of entire stars. The engineering challenges are not just difficult, but perhaps fundamentally impossible. Another theoretical loophole is the Alcubierre drive, a concept developed by Mexican physicist Miguel Alcubierre in 1994. Instead of moving through space faster than light, which relativity forbids, the Alcubierre drive would contract space in front of a spacecraft and expand it behind, creating a warp bubble that surfs on a wave of space-time distortion. From the spacecraft's perspective inside the bubble, it never exceeds the speed of light locally. Space-time around it is flat, but it arrives at its destination faster than a light beam taking the conventional route through unwarped space. Like wormholes, the Alcubierre drive requires exotic matter with negative energy density, distributed in a carefully controlled configuration around the spacecraft. Recent refinements to the concept have reduced the energy requirements from many times the mass of the observable universe down to perhaps only the mass of Jupiter, still impossibly beyond our capabilities. The drive also faces severe practical obstacles. It might be impossible to turn on or off from inside the bubble, and radiation accumulated during travel might incinerate the destination upon arrival. The distances between stars make interstellar travel extraordinarily daunting, even if we restrict ourselves entirely to known physics and accepted engineering principles. A spacecraft traveling at 10% the speed of light, or 0.1 c, approximately 30,000 kilometers per second, which is far beyond our current capabilities, would take 42.4 years to reach Proxima Centauri. At 1% the speed of light, 3,000 kilometers per second, more achievable but still enormously challenging, the journey would take 424 years, longer than European settlement in the Americas, longer than most nations have existed. The travelers would need to be placed in some form of suspended animation or cryogenic preservation, technologies we have not yet developed for human beings, or the mission would need to be multi-generational, with children born aboard the spacecraft to replace crew members who died, and those children having their own children across perhaps a dozen generations before arrival. The challenges are not merely technological, but biological, psychological, and social. Humans evolved on Earth over millions of years, adapted to Earth-specific gravity of 9.8 ms2, Earth's atmospheric composition of 78% nitrogen and 21% oxygen at 1 atmosphere pressure, Earth's 24-hour day-night cycle, Earth's complex ecosystems. We do not know whether humans can thrive physiologically and psychologically across multiple generations in the confined environment of a spacecraft, perhaps a few hundred meters in length. Muscle atrophy and bone density loss in microgravity occur at rates of 1 to 2% per month despite exercise, raising questions about whether centrifugal artificial gravity is sufficient. Radiation exposure from cosmic rays and solar events poses severe health risks without Earth's protective magnetic field and thick atmosphere. Psychological stress from confinement, isolation, and the knowledge that you will never see Earth again, that your entire life will be spent in a metal cylinder hurtling through the void. These are not trivial concerns. And even if we could build a viable generation ship, addressing all the technological and biological challenges, would it be ethical to sentence people to live their entire lives in transit, never setting foot on a planet, born into a mission they did not choose? What happens if conflicts arise aboard the ship? What if the mission needs to be aborted? There is no turning back once you've traveled for decades. These are profound ethical questions without clear answers. Yet despite these formidable obstacles, there are serious proposals for interstellar missions being actively developed. The Breakthrough Starshot Initiative, announced in 2016 and funded by investor Yuri Milner and supported by physicist Stephen Hawking, proposes using an array of powerful ground-based lasers with a combined power of 100 gigawatts to accelerate tiny, lightweight probes, each weighing only about 1 gram, roughly the weight of a paperclip, to 20% the speed of light, 60,000 kilometers per second. These Starship probes would consist of a light sail several meters across and a tiny payload containing cameras, sensors, and communication equipment, all miniaturized using advanced nanotechnology. At 20% light speed, these probes could reach Proxima Centauri in approximately 20 to 25 years after launch, plus another 4.24 years for their data to return to Earth via radio signals. The probes would not slow down upon arrival. Decelerating would require just as much energy as accelerating, so they would whip past the Proxima Centauri system at 60,000 kilometers per second, taking measurements in high-resolution photographs during a flyby lasting perhaps a few hours as they traverse the system from one side to the other before continuing into the void beyond. The data would be transmitted back to Earth using a tiny laser, taking another 4.24 years to arrive. Even this comparatively modest proposal faces enormous challenges that may prove insurmountable. The probes would need to be incredibly light while still containing functional electronics capable of surviving decades in space. They would need to survive the intense acceleration phase of perhaps 10 minutes, experiencing forces of tens of thousands of dyes. They would need to survive the absolute cold of interstellar space at perhaps 3 Kelvin, and potential collisions with interstellar dust particles. At 20% light speed, a collision with a grain of dust only 0.1 millimeters across would release kinetic energy equivalent to a bullet, potentially destroying the probe instantly. The laser system required to accelerate them would need to be immensely powerful. 100 gigawatts is roughly the total electricity generation capacity of a large nation, and would need to be precisely aimed to within microradians to hit a target several meters across. And all of this assumes no unforeseen obstacles, no unknown physics, no unexpected engineering complications. If Breakthrough Starshot succeeds in launching its first probes, perhaps in the 2040s or 2050s, assuming continued funding and technological progress, the first data from Proxima Centauri would return to Earth in the 2060s or 2070s. The people who designed and built the mission, many of whom would be in their 30s and 40s when the project begins, might not live to see its results if they are in their 80s or 90s when data returns. This is fundamentally different from robotic missions within our solar system, which provide data within hours, Moon, days, Mars, months, Jupiter, or at most years, Neptune, Pluto. Interstellar exploration requires a profound commitment across generations, a willingness to begin projects that we will not see completed, to plant trees knowing that others will enjoy their shade. This multi-generational perspective was common in the past and remains so in certain contexts. Medieval cathedral builders in Europe knew they would not see their cathedrals completed. Construction of Notre Dame de Paris took 182 years from 1163 to 1345, and the builders who laid the foundation never saw the finished edifice. The same spirit was present in the builders of the Great Wall of China, constructed over more than 2,000 years. The same commitment might be necessary for interstellar exploration. We launch probes, knowing that others, perhaps our grandchildren or great-grandchildren, will see the data and reap the benefits of our investment. But even if we send probes to every nearby star, even if we eventually develop the technology for crewed interstellar missions over the next few centuries, the distances involved mean that humanity's cosmic neighborhood will always be small relative to the size of the galaxy. The Milky Way contains an estimated 200 to 400 billion stars spread across 100,000 light-years. Even if we could somehow visit one star per year, which is absurdly, impossibly optimistic, given the decades to centuries required for each journey, it would take 200 to 400 billion years to visit them all, far longer than the current age of the universe at 13.8 billion. Years, longer than the sun will exist before becoming a red giant in 5 billion years, longer than the most optimistic estimates for the persistence of technological civilization. And the Milky Way is just one galaxy among an estimated 200 billion to 2 trillion galaxies in the observable universe. The distances between galaxies are even more overwhelmingly daunting than the distances between stars within a galaxy. Andromeda, our nearest large galactic neighbor, is 237 million light-years away, a distance of approximately 2.410 or 19 kilometers. Even traveling at the speed of light, which is impossible for anything with mass according to relativity, the journey would take 237 million years. At the realistic speeds we've discussed for interstellar probes, 1 to 10% of light speed, it would take 25 to 250 million years, timescales comparable to the age of the dinosaurs or the time since complex life emerged on Earth. Intergalactic travel is not just impractical, but effectively impossible for any civilization bound by known physics. This means that if intelligent civilizations exist elsewhere in the universe, and statistical reasoning suggests they should, given the sheer number of stars, 10 or 24 in the observable universe, and planets, current estimates suggest 1 to 2 planets per star on average, giving perhaps 10 or 24 planets, we will probably never meet them in person. Even detecting their electromagnetic signals would be extraordinarily difficult given the inverse square law of radiation and the vast distances involved. Radio waves, like all electromagnetic radiation, travel at the speed of light, so a signal from a civilization 1,000 light-years away tells us about events that occurred 1,000 years ago, around the time the Vikings were exploring North America, or the Song dynasty ruled China. If that civilization went extinct in the meantime, we would not know for another 1,000 years when the absence of continued signals finally reached us. The search for extraterrestrial intelligence, SETI, has been scanning the skies for artificial radio signals for more than 60 years since Frank Drake's Project Ozma in 1960, and has found nothing conclusive despite monitoring millions of frequencies across thousands of star systems. This is sometimes called the Fermi paradox, named after physicist Enrico Fermi, who allegedly asked over lunch in 1950, "Where is everybody?" If intelligent life is common in the galaxy, and if such life tends to develop technology and explore space as we have, why haven't we seen any evidence of it? Why no radio signals, no obviously artificial structures, no signs of stellar engineering or terraforming? There are many possible answers to the Fermi paradox, each sobering in its own way. Perhaps intelligent life is extraordinarily rare, arising perhaps once per galaxy or once per 100 galaxies. Perhaps civilizations invariably tend to destroy themselves before they can colonize space, succumbing to nuclear war, environmental collapse, or technological catastrophe. Perhaps they exist but choose not to broadcast their presence, fearful of hostile civilizations. Perhaps they communicate using methods we have not thought to look for, neutrino beams, gravitational waves, or technologies we cannot even imagine. Or perhaps the distances are simply too great, the stars too far apart, and even if the galaxy is filled with civilizations, they are so separated in space that they never encounter each other, like ships passing in the night across an ocean the size of a galaxy. This last explanation is particularly sobering. It suggests that the universe might be filled with intelligence, consciousness, philosophy, art, science, civilizations, pondering the same questions we are. And yet we are all isolated from each other by the sheer vastness of space, by the tyranny of the light speed limit. We are like islands in an infinite ocean, separated by distances measured in years and centuries that cannot be crossed in any practical sense. We can send messages in bottles, radio signals into the void, but we should not expect replies within our lifetimes or even within the lifetimes of our civilizations. The cosmic distances that isolate us physically might also isolate us temporally. Advanced civilizations might exist at different times with no overlap. A civilization might have flourished when the universe was 8 billion years old, built wonders that would astound us, persisted for 100 million years, then gone extinct through internal collapse or external catastrophe, all before our sun even formed from its molecular cloud 4.6 billion years ago. Another civilization might arise 5 billion years in the future, long after our sun has died and Earth has been sterilized, and will never know we existed. We might never overlap in time, ships passing in the night not just across space, but across billions of years of cosmic history. This temporal isolation is compounded by the finite speed of light and the relativity of simultaneity. Even if we could somehow compile a catalog of every civilization that has ever existed anywhere in the universe, we could never create a snapshot of all civilizations that exist now, because now has no absolute meaning across cosmic distances. The universe does not have a single objective present moment that all observers can agree upon. There is only the local present, the here and now that we experience directly, and the backward-looking past we observe when we look at distant galaxies. The present moment. The observatory sits on a mountaintop at an elevation of 4,205 meters, 13,996 feet, far above most of Earth's atmosphere and far from the light pollution of cities, beneath skies so dark that the Milky Way casts visible shadows on the ground. This is Mauna Kea in Hawaii, or perhaps Cerro Paranal in Chile's Atacama Desert at 2,935 meters, or the peaks of the Canary Islands, places where astronomers come to peer into the depths of space using telescopes that cost between 100 million and 10 billion and represent the cutting edge of human technology. Tonight, a telescope with a primary mirror 8 to 10 meters in diameter is pointed at a seemingly empty patch of sky barely larger than the apparent size of the moon, collecting photons that have been traveling for 12 billion years, for most of the age of the universe. The astronomer monitoring the observation sits in a control room, possibly thousands of miles away via remote connection, looking at data streaming across multiple screens in real time. What the telescope sees is nothing like what you would see with your naked eye if you looked through an eyepiece, which modern research telescopes don't even have. The telescope works primarily in infrared wavelengths between 1 and 5 microns, 0.1 to 0.05 millimeters, detecting thermal radiation from objects so far away that their visible light at 400-700 nanometers has been stretched into the infrared by cosmological redshift factors of 2, 3, or even 10. The detectors, cooled to 77 Kelvin, liquid nitrogen temperature, or even 4 Kelvin, liquid helium temperature, to reduce thermal noise, capture perhaps a few dozen photons per second from the most distant galaxies. Photons that left their source when the universe was a fraction of its current age. To the telescope's sensors, the distant universe glows in false color, translated by sophisticated image processing algorithms into images human eyes can parse and interpret. The data represents wavelengths our eyes cannot see, converted into visible colors on computer screens, infrared rendered as red, near-infrared as orange. The boundaries arbitrary but functional. Without this translation, we would be blind to most of the distant universe, unable to see the ancient galaxies whose light has been redshifted beyond the violet limit of human vision at 380 nanometers. On the screen, galaxies appear as smudges, spirals, ellipticals, and irregular forms, each one a city of stars spanning 10,000 to 200,000 light-years in diameter and containing anywhere from 10 million stars in dwarf galaxies to more than 1 trillion stars in the largest ellipticals. Some galaxies are blue in the processed images, indicating young hot stars with surface temperatures of 10th into 50,000 Kelvin in active star formation, producing perhaps 10 to 100 new stars per year. Others are red, containing older, cooler stars with temperatures of 3,000 into 6,000 Kelvin and less gas available for making new stars, perhaps only 0.1 to 1 solar mass of new stars per year. A few show signs of violent activity. Active galactic nuclei with jets of relativistic plasma streaming from supermassive black holes at their centers, black holes with masses of 1 million to 10 billion times the sun's mass, powered by accretion disks where matter spirals inward at nearly the speed of light, heated to temperatures exceeding 100,000 Kelvin, emitting more energy than entire galaxies. The astronomer is measuring the redshifts of these galaxies using spectrographs that split their light into component wavelengths, determining how far away they are by identifying characteristic spectral lines. Hydrogen's Lyman alpha line at 121.6 nanometers, or oxygen emission lines, or the Balmer series, and measuring how much those lines have been shifted toward longer wavelengths. One galaxy shows a redshift of Z^3, meaning its light wavelengths have been stretched by a factor of 4 since 1 PYZ4. This galaxy existed when the universe was only about 2.2 billion years old, approximately 16% of its current 13.8 billion year age. The light from this galaxy has been traveling for more than 11.5 billion years, crossing a distance that has expanded to roughly 21 billion light-years due to cosmic expansion. When that light left the galaxy, Earth did not yet exist. Our planet would not form for another 6.9 billion years. The solar system was still a cloud of gas and dust in the molecular cloud from which it would eventually collapse, orbiting a young Milky Way galaxy that looked quite different from today's mature spiral. This is deep time, measured not in centuries or millennia, but in giga-years, billions of years, and eons spanning substantial fractions of the universe's total age. The scales involved make human history seem like an eye blink, a fleeting moment barely worth noting. The pyramids at Giza were built approximately 4,500 years ago during Egypt's 4th dynasty, which seems profoundly ancient to us, representing 90 generations of human lifetimes. But 4,500 years is effectively nothing on cosmic scales, barely 0.01% of the age of Earth for 54 billion years, barely 0.33% of the age of the universe, 13.8 billion years. All of recorded human history, from the first cuneiform tablets in Mesopotamia around 3400 BCE to the present day, roughly 5,400 years, occupies less than 1/10,000,000th of cosmic history. Carl Sagan, the astronomer and science communicator who died in 1996, popularized the concept of the cosmic calendar in his 1977 book The Dragons of Eden and his 1980 television series Cosmos. This thought experiment compresses the entire 13.8 billion year history of the universe into a single year of 365 days, making cosmic timescales comprehensible to human minds. On this calendar, where each day represents approximately 38 million years and each second represents about 438 years, the Big Bang occurs at the first microsecond of January 1st at midnight. The Milky Way galaxy coalesces from primordial hydrogen and helium clouds around mid-March, roughly March 15th. The solar system appears in early September, September 9th. The first single-celled life on Earth emerges in late September, around September 21st. Photosynthetic cyanobacteria that would eventually produce Earth's oxygen-rich atmosphere arise in early October. Complex multicellular life doesn't appear until mid-November. The Cambrian explosion of biodiversity occurs around December 17th. The first plants colonize land on December 20th. Dinosaurs appear on December 25th, Christmas Day, and dominate Earth for 5 days before going extinct on December 30th at around 6 a.m., victims of the Chicxulub impact that released energy equivalent to 10 billion Hiroshima bombs. Anatomically modern humans, Homo sapiens, appear at approximately 11:52 p.m. on December 31st, just 8 minutes before midnight. Agriculture is invented at 11:59 and 20 p.m., a mere 40 seconds before the year ends. The pyramids are built at 11:59:50 p.m. The entire history of ancient Greece, Rome, Christianity, Islam, the Renaissance, the Industrial Revolution, and the modern era occurs in the last 10 seconds before midnight. Your entire lifetime, if you're 40 years old, occupies the last 0.09 seconds, less than 1/10 of a second on the cosmic calendar. This compression reveals with startling clarity how young we are as a species, how brief our existence has been relative to cosmic time, how recent our civilization is in the grand scheme. We are newcomers, late arrivals to a universe that has been evolving for almost 14 billion years. And yet in that brief span, those final 8 minutes of the cosmic year, we have accomplished something genuinely remarkable and perhaps unprecedented in our corner of the universe. We have figured out where we are in space and time, when we are in cosmic history, and how we came to be. We have measured the age of the universe to within 1% accuracy, 13.723 billion years. We have measured its size, at least the observable portion, at 93 billion light-years in diameter. We have traced our lineage back to the first stars that formed 100 to 200 million years after the Big Bang. We have understood through spectroscopy and nuclear physics that we are made of star stuff, that every atom in our bodies heavier than hydrogen, which comprises about 10% of your body's atoms, was forged in the nuclear furnaces of stars that died billions of years ago. This knowledge is astonishingly recent. The entire edifice of modern cosmology is less than 100 years old. Before the scientific revolution beginning around 1550 CE, humans understood almost nothing about cosmic distances or timescales. The ancient Greeks, despite their sophisticated geometry and mathematics, thought the stars might be affixed to a celestial sphere only a few million miles away, perhaps 10 to 20 times farther than the moon. Ptolemy's Almagest, the dominant astronomical text for 1,400 years, placed the stars at a distance of approximately 20,000 Earth radii, or about 130 million kilometers, coincidentally close to the actual Earth-Sun distance, but applied to the wrong celestial objects. Medieval scholars, working within Christian cosmology, debated whether the universe was 6,000 years old, based on biblical chronologies calculated by Archbishop James Ussher in 1650 as creation occurring in 44 BCE, or perhaps millions of years old. Neither estimate approached the truth by even a factor of 1,000. As recently as the early 20th century, around 1920, most astronomers believed the Milky Way was the entire universe, and that it was only a few thousand light-years across, underestimating its true diameter of 100,000 to 120,000 light-years by a factor of 20 to 40. The Great Debate of 1920 between astronomers Harlow Shapley and Heber Curtis concerned whether spiral nebulae like Andromeda were nearby gas clouds within our galaxy or distant island universes separate from our own. Shapley argued for a large Milky Way with spiral nebulae inside it. Curtis argued for a smaller Milky Way with spiral nebulae as external galaxies. Curtis was essentially correct, though Shapley's larger estimate for the Milky Way's size proved more accurate than the prevailing wisdom of the time. Our current understanding emerged through countless painstaking observations and calculations, each one pushing the boundaries of the known universe incrementally farther, each measurement built upon previous measurements in a careful edifice of knowledge. In 1610, Galileo Galilei turned his telescope, a simple refracting design with a 37mm objective lens, to the heavens, and discovered 4 moons orbiting Jupiter, Io, Europa, Ganymede, and Callisto, now called the Galilean moons, proving that not everything orbited Earth and dealing a serious blow to the geocentric Ptolemaic model. In 1838, Friedrich Wilhelm Bessel measured the parallax of the star 61 Cygni at 0.314 arcseconds, modern value 0.286 arcseconds, proving that stars were light-years away, specifically 10.3 light-years in his calculation, modern value 11.4 light-years, and establishing the first rung of the cosmic distance ladder. In 1924, Edwin Hubble identified Cepheid variable stars in the Andromeda Nebula, M31, and used Henrietta Swan-Leavitt's period luminosity relationship to calculate its distance at approximately 900,000 light-years, later refined to 2.5 to 37 million light-years with improved calibration, proving definitively that Andromeda was a separate galaxy far beyond the boundaries of the Milky Way. Each of these discoveries was met initially with skepticism and sometimes active resistance from the scientific community and the broader public. People do not easily abandon their intuitions about the universe, their comfortable sense of cosmic scale and humanity's place within it, even when confronted with compelling evidence. When Giordano Bruno suggested in the late 16th century, around 1584, in his work On the Infinite Universe and Worlds, that the stars might be distant suns with their own planetary systems, potentially harboring other worlds and other life. He was eventually burned at the stake by the Roman Inquisition in 1600, though admittedly for multiple heresies, including denial of several core Catholic doctrines, not solely for his cosmological views. When Hubble announced in 1924 that Andromeda was a separate galaxy at an enormous distance, many astronomers refused to believe him initially, despite the clear evidence from Cepheid variables. Scientific revolutions require not just evidence, but overwhelming evidence, repeated confirmation, and often a generational change as older scientists, wedded to previous models, retire, and younger scientists trained in the new paradigm take their place. The resistance is psychologically understandable. Cosmic distances violate our evolved intuitions about space and scale. We are biological organisms built by natural selection to navigate environments of meters and kilometers, to track objects moving at human speeds of a few meters per second, to hunt prey and gather resources across territories of perhaps 100 to 1,000 square kilometers. Our brains did not evolve to comprehend light years spanning trillions of kilometers or billions of years stretching across timescales longer than any evolutionary process that shaped our cognition. These scales are so far removed from everyday sensory experience that they feel abstract, unreal, almost fictional, even when we know intellectually and accept based on scientific evidence that they are objectively true descriptions of reality. Psychologists and behavioral economists have studied this cognitive limitation extensively, often calling it scope insensitivity or scope neglect. People have difficulty distinguishing between large numbers beyond a certain threshold, treating them as essentially equivalent. The difference between 1 million and 1 billion seems small intuitively to most people, even though a billion is literally 1,000 times larger. The difference between 1,000 and 1,000,000, between 11.5 days and 31.7 years, between being able to count to a number in 11 days versus 31 years. Applied to cosmic scales, this means that most people cannot truly grasp, cannot viscerally feel, the difference between a light year, 946 trillion kilometers, and a billion light years, 946 by 1021 kilometers. Both are simply very far beyond human comprehension, functionally equivalent in our intuitive sense of distance despite differing by a factor of a billion. This cognitive limitation has profound consequences for how we think about space exploration, how we set priorities for space programs, and how we conceptualize our place in the universe. When people hear that the nearest star system, Alpha Centauri, is 4.37 light-years away, they often think this sounds manageable, achievable, within the realm of possibility for future technology. They do not immediately realize that at current spacecraft speeds, the Voyager 1 probe traveling at 61 kilometers per hour relative to the Sun, the journey would take approximately 73,000 years, more than 3 times longer than human civilization has existed, longer than Homo sapiens has existed as a species, if we date our origin to 300,000 years ago. When people hear that the observable universe is 46.5 billion light-years in radius, they tend to nod along without truly comprehending what that number means. That light, traveling at 2,989 and 792 kilometers per second, takes 46.5 billion years to traverse that distance, far longer than the universe's actual age of 13.8 billion years, a fact explained by cosmic expansion. Perhaps this cognitive limitation explains why science fiction is so popular and so influential in shaping public perceptions of space. Stories like Star Trek, which premiered in 1966, and Star Wars, 1977, present a universe where interstellar travel is routine and rapid, where you can hop between star systems as easily as we drive between cities, covering distances of dozens or hundreds of light years in days or weeks using warp drives or hyperspace. The USS Enterprise travels at warp 5, which in Star Trek canon corresponds to 214 times the speed of light, allowing the crew to traverse 214 light years in 1 year, making the galaxy feel accessible. The Millennium Falcon in Star Wars jumps through hyperspace, crossing the galaxy in hours or days. These stories satisfy a deep human psychological need to explore, to see what lies beyond the horizon, to venture into unknown territories, impulses that served our ancestors well when exploring Earth, but that cannot be satisfied on cosmic scales. But these stories also fundamentally mislead us about the true nature of cosmic distances and the laws of physics that govern our universe. They make space seem smaller, more accessible, more conquerable than it actually is. They present faster-than-light travel as merely an engineering challenge to be solved, rather than as a potential physical impossibility that violates the causal structure of space-time itself. They suggest that the galaxy or even the universe is humanity's to explore and settle, when in reality we may be permanently confined to our solar system or at best a handful of nearby stars over timescales of tens of thousands of years. This gap between science fiction and scientific reality creates a subtle but persistent disappointment when people learn the actual constraints imposed by physics. The reality is far stranger, far more isolating, and in some ways far more magnificent than fiction. We are trapped on Earth, at least for now, and likely for centuries to come, orbiting an average G-type main sequence star, spectral class G2V, with a mass of 1.989 x 10 or 30 kilograms and a luminosity of 3.8 x 10 to 26 watts, located in an average location within an average spiral galaxy, about 26,000 light-years from the galactic center in the Orion Arm, a minor spiral arm between the larger Sagittarius and Perseus arms. We are separated from the nearest potentially habitable exoplanet, perhaps Proxima Centauri b, a planet 1.17 times Earth's mass orbiting Proxima Centauri every 11.2 days in its star's habitable zone, or perhaps Kepler 400 b, a super-Earth 2.36 times Earth's mass orbiting a K-type star 1,206 light-years away. Distances that might as well be infinite given current and foreseeable technology. If there is other intelligent life out there in the universe, and statistical arguments based on the Drake equation and the sheer number of stars, 1024 in the observable universe, and planets, estimated at 10.24 planets, roughly 1-2 per star on average, suggest there should be, we will very likely never meet them in person, never shake their hands or tentacles, never walk on their worlds. We might detect their electromagnetic signals, radio waves or optical pulses, if they choose to broadcast and if we happen to be listening in their direction at the right frequencies at the right time. We might send messages that arrive centuries or millennia after we are gone, messages that might receive replies millennia after our civilization has collapsed. But meaningful exchange, conversation, dialogue, cultural interaction, these seem functionally impossible across light years of distance, with communication delays measured in years or centuries. This profound isolation has led some philosophers and scientists to suggest that Earth is more precious, more valuable, more worthy of protection than we typically acknowledge in our daily lives. We are, as far as we currently know despite decades of searching, the only place in the observable universe where life has emerged and evolved to the point of self-awareness, abstract thought, symbolic language, and scientific understanding. We are the only consciousness that has measured the universe's size and age, composed symphonies and painted masterpieces, written poetry and philosophy, developed mathematics and physics, built particle accelerators and space telescopes. If we destroy ourselves through nuclear war, arsenals still contain approximately 12 out of 500 nuclear warheads globally as of 2024. Or environmental catastrophe. Global average temperature has increased 1.1 Kelvin since pre-industrial times. Or any of the other existential risks we face, engineered pandemics, artificial intelligence alignment failures, runaway nanotechnology. We might be extinguishing the only light of intelligence and consciousness in this entire region of space, spanning perhaps thousands of light years. The astronomer Carl Sagan expressed this perspective with unusual eloquence in his famous reflection on the pale blue dot photograph taken by Voyager 1 on February 14, 1990, from a distance of 6.4 billion kilometers, about 40.5 times the Earth-Sun distance beyond the orbit of Neptune, showing Earth as a tiny speck. 12 pixels in size, suspended in a sunbeam against the darkness of space. Sagan wrote, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives, on a mote of dust suspended in a sunbeam." He continued, reflecting on how this image underscores our responsibility to deal more kindly with one another, to preserve and cherish the pale blue dot, because it is the only home we have ever known, and likely the only home we will ever have. His words resonate across decades precisely because they acknowledge simultaneously our cosmic isolation and insignificance. We are infinitesimally small in space and time, while simultaneously affirming our meaning and importance. We are all we have, and that makes us infinitely precious. But let us return to the observatory, to the astronomer studying distant galaxies through the mediation of computers and detectors, to the present moment of scientific observation. The data streaming across the screens represents more than just photons from faraway places, more than just light that has traveled for billions of years. It represents the universe's history, its evolution and development, encoded in the wavelengths and intensities of electromagnetic radiation. By studying galaxies at different distances and therefore different look-back times, astronomers can watch the universe evolve over cosmic time, can see how galaxies formed from primordial gas clouds, how they grew through mergers, how star formation rates have declined from peak rates of 10 to 100 solar masses per year in galaxies at Zeta Reticuli A3 10-11 billion years ago, to much lower rates of 1 to 10 solar masses per year in modern galaxies like the Milky Way. It is like having a time machine that only goes backward, allowing us to observe the past directly but not to visit it or influence it. The most distant galaxies we can observe with current technology, seen by the James Webb Space Telescope launched in December 2021, existed when the universe was only 200 to 300 million years old, less than 2.5% of its current age. These are the first galaxies, formed from the primordial gas left over from the Big Bang, predominantly hydrogen, 75% by mass, and helium, 25% by mass, with only trace amounts of lithium and essentially no heavier elements. These early galaxies were smaller than modern galaxies, typically 1,000 to 10,000 light-years across compared to the Milky Way's 100,000 light-years. They were more irregular in shape, lacking the elegant spiral structure or smooth elliptical forms of mature galaxies. They were filled with massive hot stars with masses of 20 to 100 times the Sun's mass, with surface temperatures of 30,000 to 50,000 Kelvin, stars that lived fast, only 3 to 10 million years from formation to death, and died young in spectacular supernova explosions, releasing 10 to 44 joules of energy, briefly outshining entire galaxies. When these massive stars exploded as supernovae, they enriched the interstellar medium with heavy elements, carbon, nitrogen, oxygen, silicon, iron, and dozens of others produced through nuclear fusion in stellar cores and in the extreme conditions of the supernova itself. These elements, produced at rates of perhaps 0.1 to 0.1 solar masses of heavy elements per supernova, would eventually be incorporated into later generations of stars and the planets that formed around them. This process of stellar nucleosynthesis and chemical enrichment has been occurring for more than 13 billion years, gradually increasing the metallicity, the fraction of heavy elements, of the interstellar medium from essentially zero after the Big Bang to approximately 2% in the Sun's vicinity today. Our own solar system is made from this recycled material, assembled from a molecular cloud that collapsed 467 billion years ago. Every atom of carbon in your body, comprising about 18% of your body mass, the backbone of organic chemistry, was forged in the core of a star through the triple alpha process at temperatures exceeding 100 million Kelvin, where 3 helium nuclei fused to form carbon-12. Every atom of oxygen, 65% of your body mass, essential for water and metabolism, was created through helium fusion at even higher temperatures in more massive stars. The nitrogen in your DNA and proteins, the phosphorus in your ATP and cell membranes, the sulfur in some amino acids, all were created in stellar fusion reactions and expelled into space by stellar winds, mass loss of 10 or 7 to 10 or 5 solar masses per year from massive stars, or supernova explosions. You are literally, materially, demonstrably made of stardust, atoms that have been recycled through multiple generations of stars over billions of years, atoms that have traveled perhaps thousands of light years through interstellar space before being gravitationally gathered into the molecular cloud from which our solar system formed. This connection to distant stars in ancient times is more than poetic metaphor or romantic imagery. It is physical, material, empirically demonstrable through spectroscopy and nuclear physics. The iron in your blood, about 4 grams in an average adult human body, essential for hemoglobin and oxygen transport, was likely created in a core collapse supernova through rapid neutron capture, the R process, in conditions lasting only seconds, but at temperatures of billions of Kelvin. The calcium in your bones, about 1 kilogram in an adult body, providing structural support, was produced through alpha process nucleosynthesis in massive stars. The gold in any jewelry you might wear was almost certainly created in the violent collision of 2 neutron stars, each with masses around 1.4 times the Sun, compressed into spheres only 20 kilometers in diameter, colliding and merging in events that release gravitational waves and produce conditions extreme enough to synthesize heavy elements beyond iron through rapid neutron capture. These neutron star mergers occur perhaps once every 100,000 years per galaxy, making gold genuinely rare on cosmic scales. The astronomer at her computer screen knows this. Every time she analyzes data from a distant galaxy, she is studying processes that created the very atoms in her body, her telescope, her planet. The stars in that distant galaxy, seen as they were billions of years ago, might have produced elements that eventually found their way across thousands of light years of interstellar space to the molecular cloud from which our solar system formed. The distances involved are enormous, thousands to millions of light years. But the connections are physically real, traceable through the spectral signatures of elements in distant galaxies matching the elements we find on Earth. This perspective, sometimes called the cosmic perspective or the overview effect when experienced by astronauts viewing Earth from space, can be simultaneously humbling and empowering. Humbling because it reveals how small we are in space. Earth is 12,742 kilometers in diameter, orbiting a star that is one of 400 billion in our galaxy, which is one of 200 billion to 2 trillion galaxies in the observable universe. And how brief we are in time, existing for less than 0.1% of cosmic history. But empowering because it shows that we are part of something vast and ancient, that we are not separate from the universe but made of it, that we are quite literally the universe become aware of itself, matter organized in such a way that it can contemplate its own origins and ponder its place in the cosmos. The physicist Richard Feynman, in his 1963 Messenger Lectures at Cornell University, later published as The Character of Physical Law, captured this duality beautifully. He described looking at the stars and seeing beauty there, the same aesthetic appreciation that any human might feel gazing at the night sky. But he saw additional beauty invisible to those without scientific knowledge, the knowledge that those stars were enormously far away, that light takes years to travel from them at 299,792 kilometers per second, that understanding this required centuries of careful observation and mathematical deduction by thousands of scientists. The scientific knowledge, far from diminishing the aesthetic beauty as some romantics feared, enhanced and deepened it, adding layers of meaning and connection unavailable to those who knew only what their unaided senses revealed. Yet, for all our accumulated knowledge, for all the extraordinary progress of the last 4 centuries from Galileo's telescope to the James Webb Space Telescope, vast territories of understanding remain unexplored, fundamental questions remain unanswered. We do not know what dark matter is, Though it comprises approximately 27% of the universe's total mass energy content, and its gravitational effects are clearly observable in galaxy rotation curves, gravitational lensing, and large-scale structure formation. The leading candidates are weakly interacting massive particles, WIMPs, with masses perhaps 10 to 1,000 times the proton mass, or axions with masses around 10^5 electron volts. But decades of searching with increasingly sensitive detectors buried deep underground to shield from cosmic rays have not yet definitively detected these hypothetical particles. We have even less understanding of dark energy, the mysterious component that comprises approximately 68% of the universe's total mass energy content and causes the accelerating expansion of space. Dark energy appears to have a negative pressure, roughly 1 times its energy density in natural units, causing space to expand rather than contract under its influence. But what is dark energy? Why does it exist? Why does its density appear constant at approximately 6 × 10 joules per cubic meter even as the universe expands? Current physics cannot answer these questions. Dark energy might be related to the cosmological constant that Einstein introduced in 1917 and then abandoned, calling it his greatest blunder. Or it might be a new field called quintessence that varies over time. Or it might be something entirely beyond our current theoretical framework. This means that ordinary matter, the protons, neutrons, and electrons that make up atoms, the stuff of stars and planets and people, everything we can see with telescopes and detect with instruments, makes up only about 5% of the universe's total mass energy content. 95% of the universe is mysterious, made of something we have never directly detected in laboratories, something whose fundamental nature remains unknown despite its profound importance for cosmology. This is simultaneously humbling, we understand so little, and exciting, so much remains to be discovered. These mysteries matter profoundly because they determine the universe's ultimate fate. If dark energy continues to strengthen over time, with its equation of state parameter W1, the universe might end in a big rip, as discussed in Part 2, literally torn apart by runaway expansion in perhaps 100 billion years. If dark energy remains constant with W1 corresponding to a true cosmological constant, we face heat death, eternal expansion into cold darkness over 100 years or more. If dark energy somehow decreases, which no current theory predicts but which cannot be absolutely ruled out, gravity might eventually halt and reverse the expansion, pulling everything back together in a big crunch. We do not know which scenario is correct because we do not adequately understand dark energy's physical nature. The distances we have discussed throughout this exploration are not just spatial, but inherently temporal. When we look at distant galaxies millions or billions of light years away, we see them as they were in the past. The light left them millions or billions of years ago and is only now arriving at our telescopes. But we fundamentally cannot see their present state, cannot know what those galaxies look like right now in our reference frame. This creates a form of cosmic censorship, hiding current events behind a light travel time barrier that cannot be overcome. Galaxies existing right now at distances of billions of light years might be vastly different from what we observe. They might have merged with neighbors, formed new stars, developed new structures. But we cannot know this. We cannot know it until the light from those current events reaches us billions of years in the future. We see only their light-delayed ghosts, frozen images from the distant past. This censorship becomes more severe and more permanent as the universe ages and expansion accelerates. Due to dark energy driving accelerating expansion, galaxies beyond a certain distance, the cosmic event horizon at approximately 16.5 billion light-years in co-moving distance, are receding faster than light can travel in our direction. Light from these galaxies will never reach us, no matter how long we wait. They exist beyond our cosmic horizon, forever inaccessible to observation. As time passes, more galaxies will cross this horizon and disappear from view, their light redshifted beyond any possible detection. The universe we can observe is shrinking in terms of the number of galaxies accessible to us, not because it is physically contracting, but because the accelerating expansion is carrying distant regions beyond our cosmic reach at an ever-increasing rate. In the far future, an almost incomprehensibly long time from now, perhaps 100 trillion years when the last stars stop forming, or several 100 billion years when gravitational interactions have scattered most stars from galaxies, only gravitationally bound structures will remain visible from any given vantage point. The Milky Way will have merged with Andromeda. This merger will begin in approximately 4.5 billion years, and several other nearby galaxies, including the Triangulum Galaxy, M33, the Large and Small Magellanic Clouds, and perhaps a dozen smaller dwarf galaxies, forming a giant elliptical galaxy astronomers have nicknamed Milkomeda, with a total mass perhaps 2 to 3 trillion solar masses. But beyond this local merged structure, there will be only darkness. The cosmic microwave background will have been redshifted to temperatures of perhaps 10 baryon 30 Kelvin or less, effectively invisible, indistinguishable from a perfect vacuum. Distant galaxies will have vanished beyond the cosmic horizon. An astronomer in that distant epoch would have no evidence that the universe was once filled with hundreds of billions of separate galaxies spanning the observable universe. They would have no evidence of the Big Bang, no cosmic microwave background to detect, no distant galaxies showing patterns of expansion and redshift. They would likely conclude that the universe consists solely of their own galaxy, surrounded by infinite empty space, static and eternal. They would be cosmically poorer than we are, able to observe far less of the universe and its history. This should make us grateful for living when we do, in an era when the universe is still young enough to reveal its secrets, when evidence of the Big Bang remains detectable, when distant galaxies remain within our observable horizon. But it should also make us appropriately humble and contemplative. What evidence has already disappeared beyond our cosmic horizon during the 13.8 billion years since the Big Bang? What could we have learned about the universe's first moments, its earliest structures? If we had been here earlier when there's a photograph taken by the Hubble Space Telescope called the Hubble Ultra Deep Field, captured between September 24, 2003 and January 16, 2004. It shows a patch of sky in the constellation Fornax, a region that appears completely empty to the naked eye, containing not a single visible star. The patch is extraordinarily tiny, covering only 11 square arc-minutes, approximately 1/13 the diameter of the full moon, or roughly the apparent size of a 1 millimeter grain of sand held at arm's length 1 meter away. To put this in perspective, it would take approximately 12.7 million such patches to cover the entire celestial sphere of 41,153 square degrees. Yet in this minuscule region, representing about 0.08% of the total sky, the Hubble Space Telescope's Advanced Camera for Surveys and Wide Field Camera 3 detected approximately 10,000 galaxies. The exposure required 11.3 days of total observation time spread across 4 months, with the telescope pointed at this single patch for 400 orbits around Earth, collecting every possible photon from this small section of sky. The total exposure time was approximately 1 million seconds, or 278 hours, making it one of the deepest images ever taken in visible and near-infrared light. The resulting image, processed from hundreds of individual exposures, shows galaxies of every type and evolutionary stage, grand spirals with elegant arms, smooth ellipticals, irregular dwarf galaxies, galaxies in the violent process of colliding and merging, compact blue star-forming galaxies, red and dead ellipticals where star formation ceased billions of years ago. Some galaxies appear as they were only 400 to 800 million years after the Big Bang, when the universe was merely 3 to 6% of its current age. The light from these most distant galaxies has been traveling toward us for more than 13 billion years, crossing approximately 30 billion light-years of expanding space, accounting for cosmic expansion during the photon's journey, to reach the telescope's exquisitely sensitive CCD sensors. Each of those 10,000 galaxies contains on average 100 billion to 400 billion stars. Conservative estimates suggest 100 billion stars per galaxy, meaning this single patch contains approximately 1 trillion stars, or 10-12 stellar objects. Many of those stars, based on exoplanet surveys from Kepler and other missions, likely have planets. Current estimates suggest 1 to 2 planets per star on average across the galaxy. Some unknown fraction of those planets, perhaps those in the habitable zones where liquid water can exist, typically 0.5 to 2 AU from stars like our Sun, might harbor life, though we currently have no way to estimate this fraction reliably. And critically, this is just 1/12.7 millionth of the sky. Extrapolate this density across the full celestial sphere, and you arrive at approximately 100 billion to 200 billion galaxies in the observable universe. More recent estimates from deep field observations suggest potentially 2 trillion galaxies when accounting for faint distant galaxies below Hubble's detection threshold. Each galaxy is a vast island of stars separated from its neighbors by millions of light-years of space, containing on average less than 1 atom per cubic meter. These numbers are so large they functionally lose meaning for human cognition. How can anyone truly visualize, mentally picture, emotionally grasp 100 billion galaxies? How can we meaningfully comprehend distances of 10 billion light-years, spans of 9.46 a 10 or 25 meters that light takes 10 billion years to traverse? We cannot, not really, not in the visceral way we can visualize a kilometer of road or comprehend a year of seasons. We can manipulate these numbers mathematically, perform calculations with them, derive predictions, and test them against observations. But we cannot hold these scales directly in our conscious awareness the way we effortlessly visualize familiar distances and durations. They are too large, too abstract, too catastrophically far removed from the spatial scales of meters and temporal scales of years that our brains evolved to navigate during millions of years on the African savanna. Yet, these are the scales the universe actually operates on. This is objective reality, whether we can fully comprehend it emotionally or not, whether it feels real to our intuitions or remains forever abstract. The universe is not built to human scales or human needs. It is vast beyond any intuitive grasp of vastness, ancient beyond any meaningful reckoning of age, operating according to physical laws that we have only recently begun to understand over the past 400 years. And which still contain profound, fundamental mysteries that may take centuries more to resolve or may remain permanently beyond our understanding. Consider the age of the universe, 13 out of 97 billion years, with an uncertainty of only +/- 23 million years, less than 0.2% error, an extraordinary achievement in precision cosmology. This number is exceptionally well established, measured through multiple independent methods that all converge on essentially the same value. We know this age because we can measure the rate at which the universe is currently expanding, the Hubble constant at approximately 70 kilometers per second per megaparsec, and, knowing the density and composition of the universe, work backward using general relativity to when everything was compressed into an infinitely dense point, the singularity at T0. We can measure cosmic age through the cosmic microwave background radiation at 2.725 Kelvin, whose detailed temperature fluctuations encode information about the universe's age and composition through the acoustic peaks in its power spectrum. We can measure it through the ages of the oldest stars in globular clusters. Ancient stellar populations formed 13 to 13.5 billion years ago, that represent some of the first stars to form in our galaxy. All these independent methods agree to within their error bars, giving us high confidence in the 13.8 billion year figure. 13.8 billion years seems like an incomprehensibly long time, and by human standards spanning decades or human civilizational standards spanning millennia, it absolutely is. But consider that the universe might continue existing for trillions upon trillions of years, potentially forever, if the current acceleration driven by dark energy continues indefinitely. The current age of the universe, 13.8 billion years, is effectively nothing compared to its potential future duration. If we scale cosmic history to a human lifetime of 80 years, we exist only 8.5 months after the Big Bang birth. The universe is still in its infancy, early childhood at most. We exist near the very beginning of cosmic time in the opening paragraphs of a story that might continue for 10 to 100 years or longer, a number so vast that writing it requires 100 zeros. Stars will continue forming for trillions of years into the future, though at an ever-decreasing rate as available, hydrogen and helium gas is consumed by star formation and locked away in stellar remnants or expelled from galaxies by supernova-driven winds. Current star formation in the Milky Way proceeds at approximately 1.5 to 3 solar masses per year, down from peak rates of perhaps 10 to 30 solar masses per year when the galaxy was younger. Eventually, models predict perhaps 100 trillion years, 1014 years from now, the last star will form from the last available reservoir of gas, ignite its hydrogen fusion, and begin its life cycle. After that moment, no new stars will ever form anywhere in the universe. The epoch of star formation, which began 100 to 200 million years after the Big Bang and will continue for 100 trillion years, will end. The universe will grow gradually, inexorably darker as existing stars exhaust their nuclear fuel and die, transitioning through red giant phases for stars like the Sun, or exploding as supernovae for massive stars, or simply fading away for the smallest red dwarfs. Red dwarfs, the smallest and longest-lived stars with masses from 0.08 to 0.5 solar masses and surface temperatures of only 2500 to 4000 Kelvin, burn their hydrogen so slowly and efficiently that they might continue shining for 1 to 10 trillion years, far longer than the current age of the universe. The smallest red dwarfs, with masses around 0.08 solar masses at the boundary where hydrogen fusion can barely sustain itself, might persist for 10 trillion years before finally exhausting their fuel. But eventually, even these miserly efficient stars will fade. By 1014 years, 100 trillion years, all star formation will have ceased, and even the longest-lived red dwarfs will have exhausted their hydrogen and cooled into white dwarfs, or perhaps brown dwarfs, depending on their exact masses. The universe will enter what cosmologist Fred Adams calls the degenerate era, dominated by stellar remnants, white dwarfs, stellar cores supported by electron degeneracy pressure with masses around 0.6 solar masses compressed into volumes the size of Earth, neutron stars, cores supported by neutron degeneracy with masses around 1.4 solar masses compressed into spheres only 20 kilometers in diameter, and black holes, collapsed objects where gravity has overcome all forms of pressure. These objects will persist for immense, nearly incomprehensible periods of time. White dwarfs will cool gradually over trillions of years, eventually becoming black dwarfs, theoretical objects that have cooled to the temperature of the cosmic microwave background and become effectively invisible. This cooling process takes longer than the current age of the universe. No black dwarfs exist yet. But even these seemingly eternal remnants will eventually decay. Protons might spontaneously decay given sufficient time. Grand unified theories predict proton decay with lifetimes around 10^34 to 10^36 years, though experimental searches have found no evidence for this process, despite decades of observation with massive underground detectors containing thousands of tons of ultra-pure water. If protons do decay, then white dwarfs and neutron stars will gradually disintegrate over timescales of 10^36 years, converting their matter into radiation and lighter particles. Black holes will evaporate through Hawking radiation, a quantum mechanical process where virtual particle pairs form near the event horizon, with one particle escaping while the other falls in, causing the black hole to slowly lose mass and emit thermal radiation. The timescales for black hole evaporation are almost incomprehensibly vast, scaling with the cube of the black hole's mass. A stellar mass black hole of 10 solar masses would take approximately 10 to 67 years to evaporate completely. A supermassive black hole like Sagittarius A at the center of the Milky Way, with a mass of approximately 4 million solar masses, would take roughly 10 to 87 years to evaporate. The most massive black holes in the universe, with masses of 10 to 20 billion solar masses, might take 1,000 years or longer to evaporate. These numbers are so large they strain any attempt at comprehension. 10^100 is a googol, a number so vast that it exceeds the number of atoms in the observable universe, roughly 1080, by a factor of 1020, or 100 billion billion. Yet these represent the actual timescales on which the universe operates when given enough time, the timescales over which even black holes eventually dissolve into radiation. In the end, if current physics is correct and our understanding of thermodynamics holds at these extreme timescales, the universe will decay into a thin, cold soup of photons, neutrinos, electrons, and positrons at temperatures infinitesimally close to absolute zero, perhaps 10^30 Kelvin or even colder. This will be a state of maximum entropy where all free energy has been expended, all temperature gradients eliminated, all structure dissolved. Nothing interesting can happen in such a universe because interesting events require free energy, require the ability to do work, require gradients in temperature or density or some other quantity. A maximum entropy state is perfectly uniform, perfectly equilibrated, perfectly static. The universe will have wound down like a clock that has finally stopped, reaching a final state of cold, dark, featureless equilibrium called the heat death. This is the inevitable conclusion required by the second law of thermodynamics, one of the most fundamental principles in physics. Entropy, roughly speaking, disorder or the number of possible microscopic states consistent with macroscopic observations, always increases in closed systems, never decreases. The universe is by definition the ultimate closed system, the largest possible closed system containing everything that exists. Therefore, its total entropy must increase monotonically until it reaches its maximum possible value, at which point the universe achieves thermodynamic equilibrium. Once equilibrium is reached, no further change is possible because all processes that could occur have already occurred, and the universe has settled into its most probable macroscopic state. Confronting these timescales and this ultimate fate can be existentially disturbing, even devastating to contemplate. We are psychologically used to thinking of the universe as vast and eternal, permanent and unchanging on cosmic scales, even if individual objects come and go. But modern cosmology reveals that while the universe might be eternal in its temporal duration, existing forever into the future, it is finite in its capacity for interesting behavior, for complexity, for life and consciousness. The epoch of stars, planets, and life, the stelliferous era lasting perhaps 100 trillion years, is brief relative to the universe's total duration, a tiny flicker of complexity in an overwhelmingly simple universe dominated by equilibrium. Everything we care about, everything we have accomplished as a species, everything we might accomplish in millions or billions of years of future evolution, will eventually be erased without any physical trace whatsoever. The physicist Freeman Dyson, who died in 2020, once speculated in his 1979 paper, Time Without End, about whether intelligence could survive indefinitely, even as the universe approached heat death, by reducing its metabolic rate to match the decreasing available energy. Dyson proposed that intelligent beings could think slower and slower, hibernating for exponentially longer periods between thoughts, using less and less energy per computation, and thereby continue indefinitely, even as the universe cooled toward absolute zero. It was an optimistic vision, suggesting that consciousness might be eternal even if stars were not. But later analysis by other physicists, particularly Lawrence Krauss and Glenn Starkman in 1999, suggested that Dyson's scenario would not actually work given quantum mechanics and information theory. Quantum mechanics and thermodynamics impose hard limits on information processing that cannot be circumvented by any clever engineering. Specifically, to process information reliably requires maintaining quantum states against thermal fluctuations, which requires a certain minimum energy per bit of information. As the universe cools, less energy is available, and eventually there is insufficient energy to sustain even the slowest possible computation. Eventually, even the cleverest intelligence running on the most efficient possible hardware would run out of free energy and cease to function. In the very long run, given sufficient time, trillions upon trillions of years, everything ends. Consciousness, complexity, computation, life, all eventually cease as the universe approaches maximum entropy. Should this ultimate fate depress us? Should we despair at the knowledge that everything we do will eventually be erased, that the universe will inevitably decay into cold equilibrium? Some philosophers argue that it should not, that such despair misunderstands the nature of meaning and value. The fact that everything ends does not diminish its value while it exists. A beautiful sunset is no less beautiful because it fades after minutes. A delicious meal is no less enjoyable because it is consumed. A life is no less meaningful because it ends in death. The universe is no less wondrous because it will eventually decay into featureless equilibrium trillions of years from now. We should enjoy and appreciate what exists now while it exists in the present moment, rather than mourning its eventual loss in a future so distant it has no practical relevance to our lives or even to the lifespan of our species. Others find this argument philosophically unconvincing. If nothing we do has any permanent consequence, if the universe will eventually reach a state where it is exactly as if we never existed, no trace, no memory, no lingering effect of any kind, then in what sense does anything we do actually matter? What is the point of struggling, achieving, creating, building civilization if it all inevitably ends in heat death? If the ultimate answer to every human endeavor is heat death erases everything, then why should we care about anything beyond immediate pleasure? This is the existential question at the heart of modern cosmology, the problem of meaning in a finite, entropic universe, and different people answer it differently based on their philosophical commitments and psychological temperaments. But let us return from these distant futures, these abstract, thermodynamic endgames trillions of years hence, to the present moment, to the universe as it exists now in the year 2025, still young at 13 billion years old, and full of stars forming at rates of perhaps 10 to 100 solar masses per year per galaxy across billions of galaxies. We have focused extensively throughout this exploration on the vastness of cosmic distances, on their isolating and limiting effects, on how light years separate us from everything else in the universe. But there is another perspective that deserves consideration. These vast distances also protect us, serving as shields as well as barriers. If stars were closer together than they actually are, if the typical interstellar distance were measured in light months rather than light years, life might be impossible, or at least far more precarious. Stars occasionally explode as supernovae, Type II supernovae from massive stars collapsing, or Type Ia from white dwarfs, accreting matter past the Chandrasekhar limit of 1.4 solar masses. These explosions release enormous amounts of radiation, approximately 10 to 44 joules of energy, briefly outshining entire galaxies, with much of that energy emerging as high-energy gamma rays, X-rays, and ultraviolet radiation. If a supernova occurred too close to Earth, current estimates suggest within approximately 25 to 50 light-years, the intense radiation could strip away a significant fraction of our ozone layer within hours to days. The ozone layer in the stratosphere, at altitudes of 15 to 35 kilometers, absorbs most incoming ultraviolet B and ultraviolet C radiation. Without it, surface UV levels would increase by factors of 10 to 100, causing widespread damage to phytoplankton, the base of marine food chains, terrestrial plants, and animals, including humans. This could trigger a mass extinction event, killing most complex life on Earth's surface. The fact that stars are separated by typical distances of 3 to 10 light-years in the solar neighborhood means that supernovae, while common in the galaxy, roughly 2 to 3 per century in the Milky Way, rarely threaten inhabited worlds. Distance is a shield as well as a barrier, protecting us from the violent deaths of massive stars. Our nearest stellar neighbors, the Alpha Centauri system at 437 light-years, Barnard Star at 596 light-years, Wolf 359 at 786 light-years, are all small, stable stars with masses well below the 8 solar masses required to explode as supernovae. We are fortunate to live in a relatively quiet stellar neighborhood with no supernova candidates within 50 light-years. Similarly, the vast distances between galaxies, typically millions of light-years, with Andromeda at 237 million light-years being our nearest large neighbor, mean that galaxy collisions, while spectacular and dramatic, are not as catastrophic as intuition might suggest. When galaxies collide over timescales of hundreds of millions to billions of years, individual stars almost never actually collide with each other because the distances between stars within a galaxy are so large relative to stellar sizes. Stars are typically separated by distances of light-years, trillions of kilometers, while having diameters of only millions of kilometers. The Sun is 1.4 million kilometers in diameter, meaning stars are separated by distances roughly 10 million times their own size. This is like having two particles 1 centimeter in diameter separated by 100 kilometers. The probability of direct collision is infinitesimally small. The galaxies pass through each other like ghosts, their stellar components barely noticing, their stars simply finding themselves redistributed into new orbits within the merged system. The main effects of galaxy collisions are gravitational. Tidal forces distort the galaxy's shapes, creating spectacular tidal tails and bridges visible in Hubble images. Gas clouds within the galaxies do collide because gas is distributed more continuously than stars, and these collisions compress the gas, triggering intense bursts of new star formation at rates potentially 10 to 100 times higher than normal. The Milky Way and Andromeda are scheduled to begin colliding in approximately 4.5 billion years, based on Hubble measurements of Andromeda's proper motion. But the solar system will almost certainly survive intact, suffering no direct stellar collisions, merely finding itself relocated to a different position within the merged galaxy. Astronomers have nicknamed Milkomeda. These vast distances also fundamentally give the universe its large-scale structure, its ability to support complexity and interesting physics. If everything were compressed into a smaller space, if the universe were denser by factors of 10 or 100, it would be profoundly different in character. Gravity would dominate all other forces, pulling everything together into massive black holes or triggering rapid gravitational collapse. There would be no stable structures on galactic scales, no long-lived stars with stable fusion. Massive stars would form and quickly die, no planets orbiting in stable configurations for billions of years, no quiet environments where life could evolve over geological timescales. The universe would either collapse into itself in a big crunch or remain a featureless hot plasma unable to cool enough for atoms to form, or fragment immediately into black holes. The fact that the universe is mostly empty space, with an average density of approximately 5.9 protons per cubic meter, less than the best vacuum we can create in laboratories, with matter concentrated into rare islands of structure separated by enormous distances, is precisely what allows complexity to exist. This observation relates to what physicists call the fine-tuning problem. The fundamental constants of physics, dimensionless numbers like the fine structure, constant A, 1137 determining the strength of electromagnetic interactions or the ratio of electron, mass to proton mass at 1 1836 or the strength of gravity relative to electromagnetism at approximately 10^36, appear to be precisely calibrated to allow complex structures like stars, planets, and life to form. If gravity were slightly stronger by even a few percent, the universe would have collapsed long ago in a big crunch, stars would burn too quickly to allow life to evolve, and stellar explosions would be more frequent and violent. If gravity were slightly weaker by even a few percent, galaxies and stars would never have formed from the primordial hydrogen and helium. The universe would remain a diffuse gas expanding forever, never condensing into interesting structures. The fact that these constants have the particular values they have seems remarkably fortunate, even suspicious, leading to much philosophical and scientific debate. Some physicists invoke the anthropic principle, first articulated by Brandon Carter in 1973. We observe these particular values for physical constants, because only in a universe with these values could observers exist to make observations. It is a selection effect, a form of observational bias. In universes with different constants, stronger gravity, weaker electromagnetism, different masses for elementary particles, complexity could not arise, stars would not form, life would be impossible, and therefore no observers would exist to measure the constants and wonder why they have those values. We necessarily find ourselves in a universe compatible with our existence. This explanation is logically sound, but philosophically unsatisfying to many, because it does not explain why this particular universe exists, rather than one of the presumably vast number of possible universes with different, life-incompatible constants. It explains why we see what we see, but not why anything exists at all. The multiverse hypothesis offers a potentially more comprehensive explanation, though it remains highly speculative and perhaps untestable. If there are many universes, perhaps infinitely many, each with different physical constants drawn from some distribution, then it is not surprising or requiring explanation that at least one universe exists, with constants fine-tuned for complexity and observers. It becomes a statistical inevitability rather than an improbable coincidence. We happen to exist in that rare or perhaps not so rare universe because we could not exist anywhere else. We could not possibly find ourselves in a universe incompatible with life because there would be no us to find ourselves anywhere. The multiverse remains highly speculative, lacking direct observational evidence, but it addresses the fine-tuning problem in an elegant way that makes the observed constants seem less miraculous. If the multiverse exists, as some versions of eternal inflation theory suggest, then the distances we have discussed throughout this documentary, vast and mind-boggling as they are, represent only a tiny fraction of total reality. Our entire observable universe, 93 billion light-years in diameter, containing approximately 10^24 stars across 200 billion to 2 trillion galaxies, would be just one bubble in an infinite froth of universes, each causally disconnected from all the others by the exponential expansion of space between them, each potentially with different physical constants and even different dimensionalities of space or numbers of fundamental forces. The distances between separate universes would be infinite, not just in practice but in principle. They would be separated not just by space, but by existing in fundamentally different domains of reality, different pockets of the eternal inflation, forever beyond our ability to observe or interact with. This is admittedly speculation piled atop speculation, theoretical physics venturing into metaphysics, but it emerges from serious attempts to reconcile quantum mechanics with general relativity and cosmology. The universe we observe might be far stranger than we currently imagine, operating on principles we have not yet discovered or perhaps cannot discover from our limited vantage point. Our knowledge is incomplete, our theories provisional. We have learned an extraordinary amount in the past 4 centuries since Galileo's telescope, but vast territories of understanding remain unexplored, fundamental questions remain unanswered. What we can say with high confidence based on overwhelming observational evidence is that the universe is large beyond intuitive comprehension, ancient beyond ordinary reckoning, and mostly empty. The distances between celestial objects are measured in light years, units so vast that light itself, traveling at the universe's ultimate speed limit of 299,792 kilometers per second, takes years or millions of years or billions of years to cross them. These distances isolate us from the rest of the cosmos, limit what we can observe and explore, constrain the very possibility of interstellar travel or communication. But they also protect us from cosmic violence and give the universe its structure, its capacity for complexity and life. We are extraordinarily fortunate to live in an era when we can measure these distances with reasonable precision, when the evidence of cosmic history has not yet been redshifted into complete invisibility, when distant galaxies remain within our observable horizon rather than having been carried beyond it by accelerating expansion. We can see galaxies billions of light years away, can trace the universe's evolution from the cosmic microwave background through galaxy formation to the present, can understand our place in space and time with quantitative accuracy. This knowledge is precious, hard-won through centuries of observation, theoretical work, and mathematical analysis. We should cherish it and continue building on it, continue pushing the boundaries of the known universe farther into the darkness. The astronomer at the mountaintop observatory, studying data streaming from distant galaxies on her computer screens, is part of this grand multi-generational project of cosmic understanding. She is measuring distances that our ancestors of even a century ago could not have imagined, seeing light that has been traveling since before Earth existed, contributing her small but meaningful piece to humanity's collective knowledge of the universe. Her work is part of a tradition stretching back to Galileo and beyond, to Copernicus, to Ptolemy, to the ancient Babylonian astronomers who tracked planets across the sky. A tradition of looking up at the cosmos and asking fundamental questions. What is out there? How far away is it? How does it work? How did it begin? How will it end? These questions have driven human curiosity for millennia, probably for as long as humans have been capable of asking questions at all. The answers have transformed our understanding of reality multiple times, each transformation revealing a universe far larger and stranger than our ancestors imagined. We have learned that we are small, that our planet is a tiny speck in a vast cosmos, that Earth is not the center of anything, that the universe operates on scales we are not built to comprehend. This knowledge is profoundly humbling. But we have also learned something equally important, that we are capable of understanding this vast universe despite our limitations, despite our small size and brief existence. We can measure distances we cannot travel, comprehend timescales we cannot experience, grasp concepts far removed from everyday life. We can build theories and test them, make predictions and confirm them, gradually construct an accurate picture of reality through the scientific method. We are the universe become conscious, matter organized into patterns complex enough to understand its own origins. This is remarkable, perhaps miraculous in the sense of being statistically improbable, certainly precious beyond measure. The cosmic distances we have explored throughout this documentary are not just measurements, not just numbers in scientific papers. They are statements about our place in reality, about what we can and cannot know, about the fundamental limits of exploration and the extraordinary power of understanding. Light years define the structure of the cosmos and the boundaries of the possible. They remind us that we are part of something incomprehensibly vast, yet they also affirm that through science and reason, through patient observation and careful thought, we can make sense of that vastness even if we cannot physically traverse it. In the end, perhaps the most important lesson from contemplating cosmic distances is perspective, understanding our true place in reality. We live on a small world, 12,742 kilometers in diameter, orbiting an ordinary G-type star in an ordinary spiral galaxy, separated from our nearest stellar neighbors by light years, and from most of the universe by billions of light years. We are cosmically insignificant by any objective measure, our concerns and struggles vanishingly small against the backdrop of space and time. And yet here we are, conscious and wondering, asking questions and finding answers, creating meaning in an indifferent universe that does not provide meaning. That is the human achievement, the triumph of consciousness in a cosmos that does not require consciousness to function. The universe is vast beyond comprehension, ancient beyond reckoning, destined for an end too distant to meaningfully imagine. But in this brief moment, the first fraction of the cosmic story, on this small planet orbiting an average star, we exist. We observe, we think, we understand. We reach across light years with our telescopes and our mathematics, grasping at mysteries that dwarf us. We are small, but we are not insignificant. We are the universe understanding itself, and that is truly worthy of wonder.